We are approaching the nearest star system to our Sun. This is Proxima Centauri, a stellar and planetary system that also goes by the name of Alpha Centauri c. You'll understand why it's called Alpha Centauri in a moment. We are in the constellation of Centauri, only 4.2 light-years from Earth, and therefore still in our beautiful and luminous Milky Way. The luminous object you have before you is a red dwarf. These are very common in our galaxy. They represent nearly 80% of the stars in the Milky Way. The apparent magnitude of Proxima Centauri, which is equal to 11.05, does not place it in the category of the brightest stars, the most radiant stars being of first magnitude. In fact, 85% of the energy it emits is not visible to our eyes, being mainly in the infrared wavelengths. To the naked eye, its luminosity in visible light is almost 650 times less than that of our Sun. Proxima Centauri is therefore of spectral type M5, which explains why it was only discovered in 1915. With an actual diameter of 200,000 kilometers or 125,000 miles, it is 7 times smaller than the Sun, which is 1.5 times the size of Jupiter, the largest planet in our solar system. Its mass is about 12.3% of the Sun's. But Proxima Centauri has a medium density, and its density is much higher than that of the Sun. Unlike our star, which transmits its energy to the outside by radiation, Proxima Centauri transmits it by physical movements of the plasma. The interior of this star is therefore entirely convective. The helium which is produced by nuclear fusion, instead of accumulating in the center of the star, circulates inside it. This results in a convection phenomenon which generates a permanent magnetic field. This magnetic energy is extracted from the object in the form of stellar eruptions comparable to solar flares. Some of these explosions can reach incredible dimensions, corresponding to the size of the star itself, which considerably increases its total luminosity during a certain period of time. Nearly 80% of the star's surface is active, which is far beyond the activity that we know of the Sun. This is why the temperature of its corona, even outside its peaks of activity, remains higher than that of the Sun. It reaches 3.5 million degrees Celsius, or 6.3 million degrees Fahrenheit, while our Sun does not exceed 2 million degrees Celsius, or 3.6 million degrees Fahrenheit. This violent activity is nevertheless less important than many other red dwarfs can undergo, probably because of the advanced age of this star, which is estimated at several billion years. Proxima Centauri is a planetary system. The star does not evolve alone. Far from it. It is accompanied by not one, but 3 planets orbiting it. The first, Proxima Centauri b, is a telluric planet located in the habitable zone of its host, at a distance of 7 million kilometers. Its orbital period is just over 11 Earth days. Its mass, about 1.3 times that of our Earth, and its equilibrium temperature suggest that there could be water in a liquid state on its surface. But if we assume that this exoplanet has no atmosphere, which has been destroyed by repeated stellar eruptions, no form of life could be found there. The proximity of the 2 objects probably leads to a synchronous rotation, which means that this planet permanently shows the same face to its star. As a result, Proxima Centauri b could experience very high temperatures on its exposed side, hindering the presence of liquid water, while its hidden side would be extremely cold, covered mostly by ice. But what about the regions located between these two zones? Do you believe, in case of the presence of an atmosphere, that a life is possible at the level of the Terminator, this border connecting the two faces? The second planet that orbits Proxima Centauri is a cold super-Earth of the mini-Neptune type. This is Proxima Centauri c. With a mass of 5.8 times that of the Earth, it is located at about 1.5 astronomical units from its star. Its orbital period is 1900 days, or a little more than 5 Earth years. Finally, an exoplanet, whose mass is a quarter of that of the Earth, was detached in 2022. It is Proxima Centauri d, an exoplanet distant from its host by only 4 million kilometers or 2.5 million miles. Life on this planet, which orbits in only 5 days, is fatally impossible because of its proximity to the star. Furthermore, Proxima Centauri, although discovered late, was found to belong to an even larger system. In fact, it is only the third and smallest star in a triple system, Alpha Centauri, which has been known for much longer. Do you see, not far from there, these two stars which make you eye? I suggest that we get closer to these two bright stars, Alpha Centauri A and Alpha Centauri B, which form the main duo in this triple system. They are distant from their third companion by nearly 13,000 astronomical units, or 1,950 billion kilometers, or 1,200 billion miles. This distance, which is only 5% of the distance between Alpha Centauri AB and our Sun, still suggests an orbital period of Proxima Centauri between 507,000 and 613,000 years around the main duo. The distance and its low orbital velocity explain why Proxima Centauri has long been excluded from this system, to which it is nevertheless gravitationally bound. To the naked eye, this binary system, because of the proximity of its components, appears from our Earth as the brightest star in the constellation Centauri, and the third brightest in our sky, with Sirius and Canopus surpassing it. Similar to the Sun, the two stars that compose it are respectively of class G2 and K1. Alpha Centauri A, also named Rigil Cantaris, is the largest of the stellar duo, with a mass equivalent to 1.1 solar masses and a luminosity 1.519 times that of the Sun. It is a yellow dwarf that is 10% more massive than the Sun, with a radius 22% larger. In short, you are looking at the twin sister of our Sun. Alpha Centauri B, also called Ptolemy, is slightly smaller and cooler than its companion. The mass of this secondary star is 90% of that of the Sun, and its diameter only 14%. Its luminosity is barely 45% of that of the Sun. Therefore, it has a main sequence of spectral type K, which gives it this more orange color. These two stars orbit each other in 80 years. Their orbits, slightly eccentric, bring them closer to each other by 11.2 astronomical units, or about 1.68 billion kilometers, which is the distance between the Sun and Saturn. When they move away, they can be up to 35.6 astronomical units, or 5.33 billion kilometers, or 3.1 billion miles, which is equivalent to the distance between Pluto and our Sun. Astronomy enthusiasts will have to wait until May 2035 to benefit from the next pericenter in order to observe this pair in optimal conditions. Their orbital period will then have brought them closer. But our interstellar journey gives you today the possibility to observe them as never before. So let's take advantage of it to know a little more. Do you think that this star system, which is home to stars resembling our Sun, could harbor any form of life? And why wouldn't there be, in this not-so-distant land, some hot and rocky planets with a lot of water, comparable to our Earth? If you look at the near environment of Alpha Centauri A, at first sight, no planet is visible. However, a candidate exoplanet named Candidate 1 has been studied by astronomers since 2021. Distant of about 1.1 astronomical units from the star, with a revolution estimated at 1 year, it could in fact be only a dust disk, or even an artifact. On the other hand, Alpha Centauri B could have several companions, even if they have not been confirmed by the scientific community. The first, detected in 2012, would be a planet whose mass, greater than 1.1 and 2.7 times that of the Earth, qualifies it as a super-Earth. It is called Alpha Centauri BB, or Gliese 559BB. Only this candidate orbits in a non-habitable zone with respect to its host star, on a short period of 3.24 days. Distant from 0.04 astronomical units, or only 6 million kilometers, or 3.7 million miles from its star, you can imagine that no life can develop there. The very high temperatures of this planet would be able to melt lead, but recent studies have shown that Alpha Centauri BB is actually a statistical ghost. It has therefore disappeared from the list of exoplanets. The second companion, Alpha Centauri BC, is another candidate planet that seems to evolve little further than the previous one, with an orbital period of less than 20 days. Its size, 92% that of the Earth, would have made it an ideal telluric planet. But once again, its proximity to the star that hosts it makes the presence of water in a liquid state on its surface impossible. At present, it is finally near the smallest star of this triple system, Proxima Centauri, that we are most likely to discover a habitable planet, at least in part. But let's see what the next solar systems can tell us. Although more distant, they could hold some nice surprises. Let's start with Barnard Star, which is located a little further away, in the constellation of Ophiuchus, 5.9 light-years from our Sun. Despite its proximity to our solar system, its low luminosity prevents its observation without a telescope. Indeed, it is a red dwarf of spectral type M4. In other words, it is an old lady. Of an advanced age of some 10 billion years, it presents a deficiency in metal. It contains barely 25% of the amount contained by the Sun. Moreover, it has lost a lot of its rotation energy. This one is 130 days, which is relatively slow compared to the one of the Sun, which makes it in 25 days only. Much less radiant than our Sun, it is hardly more luminous than 100 full moons cumulated. Its mass represents 17% of solar mass, and its radius 15 to 20% of the Sun's. However, this star monopolizes the sphere of scientists for various reasons. Under its calm airs, it can still show strong fits of anger, resulting in significant stellar activity. Moreover, in 1998, an intense stellar flare was observed. The temperature reached during this eruption exceeded 7,700 degrees Celsius, or 13,800 degrees Fahrenheit, more than double the temperature of the star. Barnard Star is therefore a so-called eruptive star. In addition, it is sometimes called the runaway star of Barnard. If the stars appear as fixed points in our night sky, they all move in our universe. But these movements, when compared to the scale of our human lifetimes, seem insignificant. However, Barnard Star holds a speed record. It is the fastest moving star in our Earth's sky, not following the general flow of stars around our Milky Way. To give you an idea, this star moves across our sky about one full moon width over a period of 174 years. This may seem extremely slow to you, but compared to other stars, Barnard Star feels like it is spinning through the sky, with a relative lateral speed, that is, sideways to our Sun, of 90 kilometers per second, or 55 miles per second. Its radial velocity brings it closer to our solar system at the crazy speed of 140 kilometers per second, or 85 miles per second. By the year 11,800 AD, Barnard Star should be only 3.8 light-years away from our Earth. You are probably wondering why we are visiting Barnard Star. Why are we interested in this isolated star that doesn't seem to belong to a system? In fact, Barnard Star is a small planetary system. This star, which has monopolized planet hunters for several decades, has been the subject of more than 770 observations. Astronomers saw their efforts rewarded in 2018. An exoplanet does orbit near Barnard Star. It is Barnard Star B, also known as the planet Barnard B. This rocky planet has a mass equivalent to 3.2 times that of Earth, making it a super-Earth. Distant from about 60 million kilometers or 37 million miles, twice as close to its host as the Earth is to the Sun, it revolves in 233 days. But this close distance is not enough to place it in the habitable zone of this red dwarf. The exoplanet Barnard B, compared to our Earth, receives only 2% of the energy of its star. It evolves just beyond what is called the ice line. Its surface temperature is so cold, approximately minus 170 degrees Celsius, or minus 274 degrees Fahrenheit, that the presence of liquid water is highly unlikely. This planet cannot support any form of life. Too bad. This discovery, which is the result of an important collaboration between many scientists from all over the world, follows 20 years of studies performed with 7 different instruments. However, other candidate planets are being studied in this stellar region, including Barnard Star C and Barnard Star D. But so far, no study has been able to confirm their presence. Astronomers now know that they are likely to discover many other planets of this type near red dwarfs, especially as technologies continue to progress. The only thing left to do now is to find an exoplanet that has the right conditions to support life. Let's continue our interstellar journey and reach the binary system Lumen 16, which is only 6.5 light-years away from our Sun. Composed of 2 brown dwarfs, it is located in the southern constellation of the Sails. To date, it is the closest known pair of brown dwarfs to our solar system. Their recent discovery, which dates back only to 2013, was the result of a 13-month mission by NASA's WISE spacecraft. It acquired about 1.8 million images of asteroids, stars, and galaxies. But first, what is a brown dwarf? In reality, it is an object too massive to be considered a gas giant, but not massive enough to be a star, being unable to trigger nuclear fusion at its center. Brown dwarfs are sometimes compared to failed stars. The main component of this binary system is of spectral type L8. The second, even less bright, is also a late bloomer that appears closer to the transition threshold. These two objects, which are separated by more than 3 astronomical units, orbit each other in about 25 years. This slowness is explained by their low mass, although it represents about 30 times that of Jupiter. Like Jupiter, the 2 brown dwarfs are subject to strong winds, as evidenced by the bright stripes running parallel to their respective equators. If you take a closer look at Object B, you will see a complex structure of irregular clouds on its surface, sometimes light, sometimes dark. Composed of iron droplets and other minerals, these disparate clouds present extreme weather conditions, with temperatures exceeding 1,000 degrees Celsius or 1,832 degrees Fahrenheit. But let's be careful and keep our distance from this molten iron rain. Because of their low luminosity, these 2 red dwarfs offer scientists an open-air laboratory that should allow them to study this type of object more easily. Brown dwarfs could reveal the secrets that govern planetary evolution, but also the formation of stars. They could even allow the discovery of exoplanets. While brown dwarfs are not massive enough to allow hydrogen fusion like stars do, they do cool slowly as they contract, and their surface gravity increases. As a result, the surface temperature of a brown dwarf can vary considerably. It can reach degrees almost comparable to those of a star, and on the contrary, degrees as low as those of a cold planet. Their age and their physical composition are as many parameters that make them different from each other. They can then present great diversity of colors and spectral characteristics. Slight perturbations are observable in the orbits of these 2 brown dwarfs. A planet is probably at the origin of these variations. But to find this unconfirmed object, we must know on which side to look, and at what distance. Because as we have already seen, even at very large distances from each other, objects can be linked. Let's go now to the constellation of Hydra to discover the star Y0855-0714. This star is 7.2 light-years away from our Sun. This short distance on the cosmic scale makes it the 4th closest star to our Sun. Its physical characteristics place it in the category of sub-brown dwarfs, or brown dwarfs of planetary mass, its mass corresponding to 1% of the solar mass. Its formation, identical to that of stars or brown dwarfs, is the result of the collapse of a gas cloud. Only its mass, which is 10 masses of Jupiter, remains lower than the 13 masses allowing it to generate the thermonuclear fusion of deuterium, so that it can claim the status of star. If this type of object is often classified in the category of brown dwarfs of planetary mass, some scientists consider them as planets floating freely in the cosmos. Y0855-0714 is even cataloged by some as a rogue planet, especially since it seems to evolve alone, without any companion at its side. Its discovery, made possible by WISE, NASA's Wide Field Infrared Explorer, dates back to 2014. This star, whose radius is slightly smaller than Jupiter's, has average temperatures worthy of the North Pole, from about minus 48 degrees Celsius to minus 13 degrees Celsius, or between minus 54 degrees Fahrenheit and 9 degrees Fahrenheit. Colder than Earth's average temperatures, but warmer than those on the surface of Jupiter. Therefore, among all its fellows in interstellar space, it is the coldest object of all. But this is not what surprised astronomers the most when they observed it. Let's get a little closer to this failing star. Its spectral type Y allows us to observe its surface more closely, without the need to protect our eyes. We can admire in an atmosphere tinted with azure shades, clouds similar to those surrounding our beautiful blue planet. Isn't it extraordinary? These clouds are composed of water ice crystals and sodium sulfide. This is a first for scientists. If water vapor has already been detected in the atmospheres of exoplanets, this is the first time that water clouds are observed outside our solar system. Even at the closest to our planet, these observations are generally only possible on Earth or Mars. The giant planets are so cold that the ammonia ice clouds mask the water clouds, as on Jupiter and Saturn, and the atmospheres of Neptune and Uranus prevent any visibility. All in all, this so-called failing star is of great interest to the scientific community, especially since it evolves alone in interstellar space. As you have probably noticed, no other object seems to be gravitationally linked to this failed star. Observations looking at it therefore cannot be subject to interference from a nearby star that could cause any glare. Let's now turn our attention to another star system, also located a short distance from our solar system. Let's go to the constellation Leo, where a red dwarf has, like our Sun, a corona. Here we are approaching Wolf 359, a star that is certainly quite pale, with a spectral type of class M6.5, but which hosts two exoplanets. They are respectively named Wolf 359b and Wolf 359c. Wolf 359 is one of the smallest stars known to date, its mass of 0.09 solar masses being at the lower limit. Indeed, a star whose mass is lower than 0.08 solar mass is not massive enough to ignite the hydrogen of its core. Wolf 359 is then at the limit to be considered also as a brown dwarf. Because of its small size, its radius being only 0.16 solar radius, it is entirely convective. The helium produced in its center arrives at its surface thanks to the movement of the plasma. Because of this weak and slow production of energy, it will probably remain in this state much longer than our Sun, which burns its cartridges at high speed. The life of the latter is estimated at 10 billion years, and we know that it has reached 4.55 billion years. In place of our Sun, the faintness of Wolf 359 would represent about 10 times the brightness of our full moon. Not enough to cause us the slightest sunburn, even worse, not enough to hope for any presence of life on our planet, which would then be covered with ice. However, this young spinner at least 100 million years old and whose projected rotation speed is less than 3 kilometers per second, or 2 miles per second, is a flare star. In other words, a variable star. Of UV Ceti type, it undergoes sometimes brutal increases of its luminosity on all its spectrum. Its magnetic activity induces brief eruptions which can occur at a rate of 32 events over a period of 2 hours, most of them being micro-eruptions. Its surface temperature, much lower than that of our Sun, is nevertheless 2,500 degrees Celsius, or 4,532 degrees Fahrenheit. This temperature is low enough for the chemical compounds to remain long enough to be observed with their spectral lines. In 2001, molecular lines composed of carbon monoxide, iron hydride, chromium hydride, water, magnesium hydride, vanadium oxide, or titanium oxide could be observed for the first time from a terrestrial telescope. Apart from the Sun, Wolf 359 is therefore the first star to expose the spectrum of its corona to the light. The study of its spectrum revealed the absence of lithium lines. This element has probably been entirely consumed by fusion in the core. This is the parameter that allows us to conclude that this star must be at least 100 million years old. As we have seen, Wolf 359 is not alone. It has 2 companions. 2 planets orbit around it. The first, Wolf 359b, is 276 million kilometers, or 170 million miles away, and the second, Wolf 359c, is close to 2.7 million kilometers, or 1.7 million miles. The more distant of the two has a mass of about 43.9 Earth masses and orbits Wolf 359 over a period of 2,938 days. The closer one, Wolf 359c, is much less massive, with its 3.8 Earth masses. It orbits its star in 2.7 days. Unfortunately, these 2 planets are either too far away or too close to their host to be located in the habitable zone, which extends from 3.6 and 7.7 million kilometers away, or between 2.2 and 4.7 million miles. Wolf 359b would be so cold that it could only be covered by a thick coat of ice, while its companion, Wolf 359c, would suffer from temperatures too high for water to remain in liquid state on its surface. Our efforts to find a potentially habitable exoplanet will therefore have to focus on another star system. Another red dwarf located in the Big Dipper constellation and 8.3 light-years away from our Sun is particularly promising. Let's join the second Argelander star, better known as Gliese 411 or Lalande 21185, an old lady between 5 and 10 billion years old. This red dwarf of type MV5 is cold and dark. Its luminosity, which is 6,000 times lower than that of our Sun, does not prevent it, however, from being among the brightest red dwarfs in the solar neighborhood. Its apparent magnitude is only 7.47, so it cannot be observed with the naked eye. It has all the characteristics of a half-sun, a mass of about 46% of solar mass, and a diameter equivalent to 40% of that of the Sun. If its mass had reached 50% of solar mass, it would probably have entered the category of red giants. Its surface temperature, which is about 3,328 degrees Celsius, or 6,022 degrees Fahrenheit, or 62% of that of the Sun, can undergo sudden variations as well as its luminosity. Indeed, Gliese 411 is a so-called eruptive star, a flare. The eruptions on its surface are as unpredictable as they are spectacular, especially since the excess luminosity produced contrasts with the usual pallor of the star. At first sight, apart from its spectral anger, this star has nothing extraordinary. However, it integrates the list of interesting objects for exoplanet hunters. On the one hand, because of its proximity to our Earth, and on the other hand, because of its constant radial velocity. It is a perfect example of the stability level of red dwarfs, although it moves perpendicular to the galactic plane at high speed with an average of 47 kilometers per second, or 30 miles per second. In its interstellar course, Gliese 411 undergoes, however, astrometric perturbations. The study of these variations has established that this red dwarf is indeed part of a multiple system. Since 1996, it is known that not one, but two, or even potentially three planets are in orbit around Gliese 411, which is therefore the fourth closest planetary system to our Sun, after Alpha Centauri, Barnard Star, and Wolf 359. The first planet is called Gliese 411b. It is a super-Earth. Its mass corresponds to 3 Earth masses. Very close to its star, at 0.08 times the distance Earth to Sun, it completes its orbital period, which is very circular, in only 13 days. Gliese 411b is 5 times closer to its host than Mercury is to the Sun, and although this star is less hot than the Sun, the planet is not in the habitable zone. It receives 3.5 times more energy than the Earth receives from the Sun, and must therefore have strong similarities with Venus. A second planet evolves at a little less than 3 astronomical units from the mother star. This is Gliese 411c. This exoplanet, whose mass exceeds 13 terrestrial masses, covers its orbit in 2,946 days. It is therefore a Neptune-like planet, located well beyond the habitable zone. Finally, a third planet could also interfere with the main star, placing it in the category of quadruple systems. Named Gliese 411d, it is 0.5 astronomical units away from its host. With a mass equivalent to 4 Earth masses, it has an orbital period of 215 days. It remains to be seen if its temperature and atmosphere are suitable or not for any form of life. What about you? What do you think about it? But let's leave this question aside for the moment. A star, sparkling like no other, attracts your attention, and for good reason. You are looking at Sirius, the brightest star after the Sun in our winter sky. You know, the one that flashes in the sky, reminding you of the intermittent lights of a plane at high altitude. Moreover, its name, which was not chosen at random, means bright in Greek. We find traces of its sparkling presence since the dawn of time. For the ancient Egyptians, the Nile star, as they called it, announced the periods of flooding of the river. In Chinese astronomy, it was called the celestial wolf, while the Greeks associated it with the dog of Orion, then called Sirius. This star also played a fundamental role for Polynesian navigators by serving as a landmark. The stars were their only reliable tool for orientation at sea, and Sirius, easily recognizable, marked the zenith of the most honored place of worship in the entire Polynesian region. It is located in the constellation of the Great Dog at a distance of 8.6 light-years from our own system. That is why it is also known as Alpha Canis Majoris, being the brightest star in this constellation. Its apparent magnitude is -1.46. To be clear, this negative number means that Sirius is brighter than our Sun, a magnitude of 1 being equivalent to the solar luminosity. This is why, despite a distant, but at the same time so close to our solar system on the scale of the cosmos, Sirius, which is classified in the category of white stars, appears so bright. Its brightness is punctuated by variation when observed from Earth. As you can see, however, it does not blink any more than our Sun. This effect is due to the fact that Sirius is located very low on our Earth's horizon. The light emitted by the star must therefore cross a large part of the atmosphere before reaching us. It is therefore more or less masked by the turbulence of the environment that separates us from it, hence its flickering. During our approach, if you look carefully at Sirius, you see that it is in fact a binary star. It is composed of two stars. The main one, Sirius A, is a white, slightly bluish star of spectral type A0 or A1. More luminous than our own star, it is 2.3 times more massive and 1.8 times larger than our Sun. I let you imagine the heat that reigns on its surface, its temperature being higher than 9,600 degrees Celsius, or 17,300 degrees Fahrenheit. That is to say, much more than our Sun, which burns at 5,504 degrees Celsius, or 9,930 degrees Fahrenheit. All these characteristics evoke the relatively young age of Sirius, which should not have more than 200, even 250 million years. It has for companion a white dwarf named Sirius B. The latter, because of its small size, its proximity to Sirius A, and its low magnitude of only 8, was discovered only very late in 1862. As a white dwarf, Sirius B has a size comparable to that of the Earth, while its mass is equivalent to that of the Sun, and its estimated temperatures are 3 times higher than those of Sirius A. Separated from the main star by an average of 19.5 astronomical units, or 19.5 times the distance between the Earth and the Sun, it orbits around it over a period of 50 years. Because of a strongly marked elliptical orbit, the distance between these two stars can vary from 8.1 to 31.5 astronomical units. This maximum distance will soon be reached by 2024 to 2025, while the next passage at the periastron of the system, i.e. the moment when the two stars will be the closest, is planned for 2044. This binary system is waving alone in the cosmos. No planet has yet been seen in its vicinity. Sirius being a young star, it is unlikely that exoplanets are in orbit around it. However, since 2018, NASA has been exploring this bright object with the Transiting Exoplanet Survey satellite. And who knows, its high brightness could mask one or even several planetary objects. At almost the same distance from our Sun, another stellar duo awaits us. Let's join, at 8.7 light-years from our solar system, Luyten 726-8, a binary system hosting two stars, BL Ceti and UV Ceti. They are once again two M-type red dwarfs, probably younger than our solar system. With a low luminosity, they are not visible to the naked eye. This is why they were only discovered in 1948. These two stars, like twin sisters, have many similarities. Both have almost identical masses, radii, and luminosities. Their mass is 10% of the solar mass, their radius 14%, and their combined luminosity is 11,000 times less than that of the Sun. It is therefore not surprising that we detect an identical temperature on the surface of these two stars, which is close to 2,330 degrees Celsius, or 4,220 degrees Fahrenheit. If the two stars orbit around a common barycenter over a period of 26.5 years, their orbits are marked by a strong eccentricity. The distance between them can therefore vary between 2.1 and 8.8 astronomical units, causing strong tidal forces between the two objects. BL Ceti, the main component of this duo, has a luminosity 6,000 times lower than the Sun, while the secondary star, UV Ceti, has a luminosity 4,000 times lower. UV Ceti is the better known of the two. The latter rotates very fast, with a rotation of only 0.2 days. Its rotation speed feeds a powerful magnetic field, where bubbles, charged with matter by the convection currents typical of red dwarfs, trigger important eruptions. UV Ceti is therefore a flaming star. During one of its numerous eruptions, its luminosity can be multiplied by 100 in a few seconds. At the same time, massive emissions of UV and X-rays ignite the star's environment. In 1952, the observation of UV Ceti allowed to count not less than 75 variations of its luminosity in only 20 seconds. This particularity places it in the category of variable stars, where, moreover, it serves as a reference. Indeed, other eruptive stars are sometimes included in the category of UV Ceti variables. The main star is less active. This is probably related to the fact that it has a lower rotation speed. Nevertheless, the motions of these two stars are at the origin of unusual stellar winds. Their surfaces are subjected to winds more violent than those experienced by the Sun, although weaker at equivalent distances. The resulting heliosphere extends to 10 or 20 astronomical units. During massive eruptions, this heliosphere can be expelled up to 100 astronomical units. When the eruption of one of the two stars is directed towards the second, a shock zone is created, somewhere between the two stars, giving a complex and non-spherical shape to the heliosphere surrounding UV Ceti. In short, the environment near this star system does not seem to be the most favorable to host a planet in the best conditions. This one, in addition to being subjected to stellar winds, would inexorably undergo the unpredictable explosions of anger of UV Ceti. However, oscillations have been noticed in the orbits of the two stars, in particular that of BL Ceti. But what could a planet located in this tiny part of space look like? A hypothetical planet orbiting UV Ceti would have no atmosphere, as it would be deteriorated in a few millennia by repeated flares. On the other hand, a planet orbiting BL Ceti could keep its atmosphere for more than 100,000 years. However, the important forces of tide undergone would dress this planet of a multitude of volcanoes, where the only existing rivers would welcome only the flows of a burning lava. Moreover, the strong fluctuations of temperatures would have reason of the rock present on its surface, transforming it gradually into dust, which would mix with the volcanic ashes. A planet in orbit around these two stars would be more than 30 astronomical units away. Of course, it could contain its atmosphere, but its temperatures below minus 230 degrees Celsius or minus 382 degrees Fahrenheit would not be very attractive, and the luminosity on this planet would be null, except during strong stellar eruptions. In short, if the binary system Luyten 726-8 can be attractive by its spectacular side, it is not very welcoming. Ross 154 is the 9th closest star system to our Sun. Located in the constellation of Sagittarius, it is 9.7 light-years away. Composed of a main sequence star of spectral class M3.5V, it is not visible to the naked eye from our Earth. Ross 154 is therefore, by definition, a red dwarf star, cold and dark. Its discovery by Frank Elmore Ross dates back to 1925. Ross 154, also named Gliese 729, has a mass equivalent to 17% of solar mass. Its size is about 20% of the Sun. Its apparent magnitude is only 10.44. The luminosity of this star is relatively low and represents only 0.4% of the Sun. Ross 154 is so small that it is not able to expel heat from the core at its surface, as do the larger red dwarfs. So it carries this heat to its surface by convection. Moreover, as you can imagine, the heat at its surface is much lower than that of our Sun. It is estimated at 3,019 degrees Celsius, or 5,460 degrees Fahrenheit. However, this star is not so ordinary. Like many red dwarfs, it is an eruptive star. Moreover, it integrates the category of UV Ceti-type variables. This flare star, during prodigious eruptions, can thus generate X-ray emissions comparable to, or even superior to, those of the Sun. In addition, to integrate the catalog of eruptive stars, Ross 154 is also part of the variable stars of type BY Draconis because of its variations of 0.03 magnitude, noted on a period of 2.87 days. In addition, its relatively low metallicity, estimated at 56% of that of the Sun, as well as its moderately high rotation speed of 3.5 kilometers per second, or 4 miles per second, allow to conclude that it is a relatively young star. Ross 154 is less than 1 billion years old. No planet has been detected in its environment. In any case, as for a large part of red dwarf stars, the numerous and violent eruptions which burst out at its surface would fatally harm any form of life which could develop in its habitable zone, the planet having necessarily to be close to the star. In the constellation of Andromeda, another red dwarf has almost the same characteristics. It is Ross 248, also known as Gliese 905. Located at 10.3 light-years from our solar system, it is similarly a flaming star that sometimes increases its brightness suddenly. Its mass is about 12% of the solar mass, its diameter is 7%, and its luminosity is 11,000 times lower than the Sun's. Periods of variability have been reported. ranging from 4.2 years to 120 days, and 5 others between 60 and 291 days. What if these were astrometric disturbances that could be attributed to the presence of an invisible companion? For the moment, no planet or other object has been found orbiting this star. In any case, the meteorological vagaries of this star can only harm any form of life in its proximal periphery, if it could have developed at all, especially since its reddish color would prevent any form of terrestrial-type plant life from properly carrying out its photosynthesis process. Another star system is of great interest to the scientific community. It is an orange dwarf star that plays hide-and-seek. Let's go to discover this mysterious star in the constellation of Eridanus, 10.5 light-years from our solar system. This is Epsilon Idani, also known as RAN. Its apparent magnitude of 3.73 makes it the third closest individual star system visible to the naked eye. Younger than our Sun, it is between 200 and 800 million years old. Being a main sequence star of spectral class K2, the energy generated in its entrails by the nuclear fusion of hydrogen is diffused at its surface, where the temperature is higher than 4,800 degrees Celsius, or 8,670 degrees Fahrenheit. This is what gives it its beautiful orange color. Slightly smaller than our Sun, its mass is 82% of the solar mass, and its radius is 74% of the Sun's. Its average period of rotation is 11.2 days. Epsilon Idani is thus more than twice less fast than the Sun. If its luminosity is only equivalent to 34% of the Sun's, on the other hand, it generates a level of magnetic activity higher than that of the Sun. The chromosphere and the corona that surround it are therefore much more dynamic. As a proof, the average intensity of the magnetic field at its surface is 40 times higher than that of the Sun, and its stellar winds 30 times more violent. But this activity is not regular at its surface. Some regions are much more active than others. Epsilon Idani is therefore considered as a variable BY Draconis. It is a star that has a disconcerting behavior. Sometimes it brightens, sometimes it darkens. It has cycles of 27 years during which its brightness decreases considerably over a period of about 2 years. This decrease in intensity was last seen from 2009 to 2011. What gigantic object could shadow this star so much? It is known that Epsilon is surrounded by not one, but 2 rocky asteroid belts. One, 3 astronomical units away from the star, the second, 20 astronomical units away. However, they cannot explain this particularity. In fact, Epsilon is a binary star with eclipses. This means that it is accompanied by a dark object, probably a star, or even a pair of stars, surrounded by a disk of dust, dense and thick enough to make it invisible. These 2 stars are probably 30 astronomical units apart, and the diameter of the rings surrounding this pseudo-dark star must reach 20 astronomical units, occulting the main component like a curtain. However, Epsilon still reserves us a surprise. In addition to these variations of light, a study over 20 years of its radial speed has highlighted periodic variations. This observation has allowed to highlight the presence of a giant planet of the size of Jupiter in orbit around the star. This planet, named Epsilon Idani b, or AE-Jur, follows a slightly eccentric elliptical orbit. Its semi-major axis is equivalent to the distance between our Sun and the asteroid belt. The size of this gas giant is estimated between 80 and 160% of the size of Jupiter. It completes its orbit in 7 years. If a planet could have formed in this environment, it is probably not alone, especially since the observed dust cloud has an asymmetry that could be explained by the presence of a second planet. This one would then be located much further away than the first one and would have a much longer orbital period. I now propose you to join another red dwarf. Yes, another one. Remember, red dwarfs alone account for about 80 to 85% of the stellar population in our galaxy. But this star should be of great interest to you, as it is considered by the scientific community as the best star to search for potentially habitable exoplanets. Let's discover Gliese 887, also known as Lacaille 9352. It takes the 12th place in the list of stellar systems closest to the Sun. Located in the constellation of Southern Pisces, 10.7 light-years from our Earth, it appears to be the brightest red dwarf in our sky and requires only a small telescope to be observed. Its luminosity is about 1% of that of the Sun. It is also the most massive of all red dwarfs, with nearly half a solar mass, at a distance of 6 parsecs from the Sun, or a little less than 20 light-years. But what makes this star even more exceptional is its low photometric variability, which makes it a quiet red dwarf like no other. Unlike its companions, Gliese 887 is less magnetically active and does not seem to ignite by triggering huge explosions or stellar eruptions. In other words, if there are planets orbiting in its narrow habitable zone, we could well detect traces of life there, and even, why not, consider terraforming them when technology allows it. This is very good news. On the one hand, the inactivity of this star greatly facilitates the remote observation of any exoplanetary atmosphere. On the other hand, exoplanets orbiting Gliese 887, which have not undergone many energetic explosions, may have retained their original atmosphere. What if I were to reveal to you that at least 2 exoplanets have been identified near this star? The first, Gliese 887b, is a super-Earth of about 4 Earth masses. It orbits its star in 9.3 days. Unfortunately, the small distance between it and its host, a little over 10 million kilometers, or 6.2 million miles, means that the temperature is far too high for water to be present in a liquid state. The second, Gliese 887c, is also a super-Earth, whose mass is estimated at 7 times that of the Earth. It orbits the star in 21.8 days. Do not rejoice too quickly, because unfortunately, for it too, the conditions are not optimal for it to harbor any form of life. Although a little further away from the star than the first described super-Earth, it is only 17 million kilometers or 11 million miles away. Once again, it is too close, and therefore too hot to maintain water in a liquid state, the temperature of its atmosphere having to reach at least 70 degrees Celsius or 158 degrees Fahrenheit. However, any hope of finding an exoplanet in the habitable zone of Gliese 887 is not abandoned. Moreover, a candidate planet has been located in the habitable zone of this planetary system. named Gliese 887d, this super-Earth of 8 Earth masses orbits its star in 50 days. Contrary to the 2 previous planets, it could therefore experience temperate temperatures and could therefore be well suited to the development of life. Another planetary system, also a little less than 11 light-years away, is located in the zodiacal constellation of Virgo. Let us now approach Ross 128, also named Gliese 447, the 13th closest star system to our Sun. This star has an apparent magnitude of 11.13. Its luminosity is therefore 100 times too low to be observed with the naked eye from our Earth. The primary object of the system is once again a red dwarf. Its mass is 15% of the solar mass, and its radius 21% of the Sun's. The temperature of its stellar atmosphere is 2,900 degrees Celsius, or 5,252 degrees Fahrenheit. Most of the energy radiated by the star is visible only in the infrared, with a luminosity 33,000 times lower than that of the Sun. As a result, it is of spectral type M4V, hence its typical cold orange-red color. Twice as old as our Sun, this star has been shining for over 9.4 billion years. Despite an entirely convective activity and a rotation speed considered slow, this flare star seems to have a long-term stellar activity cycle. As mentioned earlier, Ross 128 is part of a system. It hosts an exoplanet. This one, probably telluric, orbits in the interior edge of the zone of habitability and thus receives approximately 38% more sunlight than the Earth. The planet Ross 128b is therefore potentially habitable. It is, after Proxima Centauri b, the second closest exoplanet to our solar system to enter this coveted category of cosmic objects. Let's see what this satellite looks like. Slightly more massive than Proxima Centauri b, Ross 128b contains at least 1.35 times the mass of the Earth. According to its hypothetical composition, if it is composed only of pure iron, it could have a diameter equivalent to half that of our Earth. According to the opposite hypothesis, if it is only composed of hydrogen and helium, it could then measure 3 times the size of the Earth. But considering that this planet could be telluric, its radius could be 1.1 times the Earth's radius, or about 7,000 kilometers or 4,350 miles, and its mass would then be 35% more massive than that of the Earth. Depending on its atmospheric component, its surface temperature could even be approximately the same as that of our Earth. Assuming that all these parameters are green, what about those related to the orbit of this planet? Ross 128b orbits rapidly around its star in only 9.9 Earth days. This orbit is quite circular, thus having an eccentricity of only 0.036. It is more than 20 times closer to its host than the Earth is to the Sun, at a distance of 7.4 million kilometers, or 4.6 million miles. This proximity suggests that the planet has a gravity barely greater than that which we experience on Earth. But above all, it must always present the same face to its host. Apart from this particularity, this exoplanet is the only one known to date to resemble so closely our beautiful blue planet. But we must not lose sight of the fact that red dwarfs can be angry. although the Olympian calm star Ross 128 seems to behave peacefully, it could have eroded the atmosphere surrounding the planet, evolving next to it in the past, during massive and repeated eruptions. But if this is not the case, if this star has always been peaceful, then Ross 128b could well be enveloped by an atmosphere. Why not? Welcome it. We could even go so far as to consider that it could already be home to one or more extraterrestrial life forms. Our interstellar journey is coming to an end. It has taken you almost 11 light-years from our Sun. You have been able to approach the star systems closest to our Earth. In this infinitely large space, an invaluable quantity of other systems remains to be discovered. Among those already listed, some are located at a short distance. Others, on the other hand, are several million light-years away. If for the majority of them, many similarities can be noted, for others one can distinguish an unusual composition. This is particularly the case for a system that is 150 light-years away from our galaxy, the system HD 98800, or TV Craterus. This one consists of two pairs of stars, distant from each other by 150 million kilometers or 93 million miles. I let you imagine what our sky would look like with 4 suns. But what makes it even more spectacular is the disk of dust that surrounds one of these two pairs. Another system, well known to all, also presents singular characteristics. It is Alpha Ursae Minoris, more often called Polaris. You know this star well under its common name of Polaris, easily spotted near the North Celestial Pole. It is the brightest star in the Little Dipper constellation. It is 431 light-years away from our Sun. But did you know that this star is in fact a multiple star? Polaris, which is a supergiant Cepheid variable, has in fact 2 smaller companions. It is thus a triple system. It has also been found 2 other components, even more distant. Let's continue our journey towards Wolf 1061. Before going further, let's stop at 8.3 light-years from Earth, where the 4th closest exoplanet to our solar system ever detected is located, after the 3 exoplanets of the Proxima Centauri system. This exoplanet has been named GI 411b. It was detected by an international team of astronomers in 2019 at the Hot Province Observatory, thanks to the SOFI spectrograph installed on the observatory's 1.9-meter or 6 feet telescope. The telescope of the Observatory des Hautes Provinces is the one which allowed the discovery of the very first exoplanet in 1995, 51 Pegasi b. For the record, 51 Pegasi b orbits a yellow subgiant, a class of stars brighter than yellow dwarfs but less than yellow giants. It is located 51 light-years from us. At the time, no exoplanet closer to Earth had been discovered. This is not the only record that was broken by 51 Pegasi b. Astronomers also had to create a new type of planets to characterize it, because until then, no gas giant as close to its star had been discovered. 51 Pegasi b is therefore what is called a hot Jupiter. Let's go back to the 4th closest exoplanet to our solar system, GI 411b. In 2019, when it was discovered, GI 411b was the 3rd closest known exoplanet to Earth. But it has since been dethroned by Proxima Centauri d, discovered in 2022. The mass of GI 411b is equivalent to 3 times that of the Earth. It orbits the star GI 411 in the Big Dipper constellation in 13 days and is probably rocky. It is very close to its star, only 0.08 astronomical units away, about 5 times closer than Mercury to the Sun. To discover the exoplanet GI 411b, astronomers looked at the observation of red dwarfs. It is easier to find an exoplanet around a red dwarf. First, because these stars represent 80% of the stars in our galaxy. Second, because their mass, much smaller than that of the Sun, makes them more sensitive to the gravitational influence of the planets orbiting around them, which makes them more easily detectable. This is how the SOFI spectrograph detected the exoplanet GI 411b. By detecting the motions caused by the planet's mass on its star as it orbits the red dwarf. The observations gathered on GI 411b do not lean in favor of a possible life on the surface of the exoplanet. It is very close to its star, and even though red dwarfs are cooler than yellow dwarfs, it is still too close to be in the habitable zone of GI 411. It could be that this rocky planet is more like Venus than Earth. GI 411b is not a novelty for the Hot Province Observatory, which has already detected nearly 200 planets. But it is very interesting because of its proximity to our solar system. The observation of this planet in the years to come, and especially of its atmosphere, will be crucial for the astronomers, who will be able to compare their observations with the characteristics of the planets of the solar system. Thanks to its proximity to the Earth, GI 411b, like the planets of the Proxima Centauri system, can be observed directly. Let's continue our journey in the universe to discover the closest exoplanets to Earth. Not far from GI 411b is the exoplanet Ross 128b, located 11 light-years from our planet. Discovered in 2017, the exoplanet Ross 128b orbits a red dwarf, Ross 128, and was detected with the HARP spectrograph at the La Silla Observatory in Chile. It is the closest exoplanet to Earth that could potentially be inhabited, because the star Ross 168 is a rather quiet red dwarf. Its eruptions are less frequent and less violent than those of other red dwarfs, which would increase the chances of preserving the atmosphere of Ross 128b if it had one. If Ross 128b contained liquid water, it would be much more favorable to the development of life than Proxima Centauri b, which is constantly bombarded by harmful X-rays and ultraviolet radiation. Although the exact mass of Ross 128b is not known, nor its radius, astronomers have deduced that it has a low mass and is therefore probably rocky with a solid surface like the Earth. To complete these assumptions, there are models that can give us hypothetical information about this exoplanet. According to the models, Ross 128b would probably have a mass 35% greater than that of the Earth, and its radius would be 10% greater. It would receive only 38% more light than our planet, and its equilibrium temperature would be rather stable, between -60 degrees Celsius and +20 degrees Celsius, or between -76 degrees Fahrenheit and +68 degrees Fahrenheit. Its rotation period would be about 9.9 Earth days, and its rotation would be synchronous. It would orbit 20 times closer to its star than the Earth to the Sun, about 7.4 million kilometers or 4.6 million miles from its star. It is not yet known if it is located in the habitable zone of its star, because everything depends on its characteristics, in particular, on the composition and thickness of its atmosphere. It would most likely be located at the edge of the habitable zone, but nothing is confirmed yet. According to calculations, Ross 128b has a similarity index with the Earth of 0.86, which makes it the third exoplanet with the highest similarity index. The planet with the highest Earth similarity index is TRAPPIST-1b, with an ESI of 0.90, and the second planet is Kepler-438b, with an index of 0.88. But both of these planets are farther away from us, which makes Ross 128b particularly interesting for astronomers. TRAPPIST-1b remains relatively close, but is still 40 light-years away. As for Kepler-438b, it is very distant, about 475 light-years from our solar system. It is difficult at this time to study the characteristics of the atmosphere of Ross 128b because it does not transit in front of its star. To learn more about this candidate for extraterrestrial life relatively close to us, we must wait for the launch of larger telescopes, such as the ELT, the Extremely Large Telescope, built by ESO, and still under construction in the Atacama Desert in Chile. The ELT, but also the James Webb, will be able to analyze the composition of its atmosphere without using the transits method. On the other hand, here is a piece of information that should give you chills. If Ross 128b was inhabited by an advanced extraterrestrial civilization, then it could have observed the Earth in transit in front of the Sun. Potential aliens from Ross 128b know that we are here and have even had time to determine the characteristics of our planet and its atmosphere. Enough to give you a chill. Let's continue our journey into the heart of the universe in search of the closest habitable planets to Earth. YZ Ceti is a multi-planetary system located 12 light-years from Earth, just next to Ross 128b, as seen from Earth. The particularity of this star system is that scientists have discovered 3 Earth-like exoplanets. It is the second closest multi-planetary system to us, after the Proxima Centauri system. YZ Ceti is a red dwarf in the constellation Whale, which cannot be seen with the naked eye from Earth despite its relative proximity. Its mass is 13% that of the Sun, and its radius is 17% that of our star. It is an eruptive or variable star, which means that it undergoes fluctuations in brightness. In other words, its brightness can increase briefly and suddenly due to flares or stellar spots that move as the star rotates. On August 10th, 2017, was announced the discovery of 3 Earth-like exoplanets around the star YZ Ceti. It is also possible that there is a 4th planet. It would then be one of the smallest planets ever discovered. All 3 planets are too close to the star to be in its habitable zone, but they are all similar in size to Earth. According to astronomers' estimates, they would not exceed 1.5 times the size of the Earth. YZ Ceti b is the closest planet to the star. It goes around it in less than 2 days. It is very close to YZ Ceti, only 0.016 astronomical units from its star. For comparison, 1 astronomical unit is the distance between the Earth and the Sun. It is also the least massive of the 3 exoplanets in this multi-planetary system. with a mass of 0.75 times that of the Earth. YZ Ceti C is located 0.021 astronomical units of the star, and it makes the turn in 3.06 days. Its mass is 98% that of the Earth. Finally, the most distant planet from the star among the 3 exoplanets is YZ Ceti D. It is separated from its star by 0.028 astronomical units, and it goes around in 4.66 days. Its mass is estimated at 1.14 times that of the Earth. The 3 exoplanets of the YZ Ceti system were detected by radial velocity with a HARP spectrograph at the La Silla Observatory in Chile, like Ross 128b. It is not yet known if they can be observed from Earth with a transit method. Their observation would be interesting for astronomers to continue to understand the formation of planets. But unfortunately, there is little chance that these exoplanets, very close to their star, are inhabited. Not far from YZ Ceti on the scale of the universe, you can see the exoplanet Luyten b, 3rd planet with the highest similarity index to the Earth, ex Aquio, with Ross 128b. We are 12.2 light-years from Earth. This planet is also called GJ 273b. It is in orbit around a red dwarf, the star of Luyten, and it is a telluric planet. It was discovered at the same time as another planet, which also orbits the star of Luyten, Luyten C. But it is Luyten b that interests astronomers because it falls into the category of super-Earths. Its mass is equivalent to almost 3 times that of the Earth, and it receives only 6% more sunlight than the Earth. It could therefore be habitable. This is what the non-profit organization METI has sought to verify. The acronym METI stands for Messaging Extraterrestrial Intelligence, which could be translated as sending a message to an extraterrestrial intelligence. And indeed, that is the goal of this organization, to seek ways to communicate with extraterrestrials and send them messages in hopes of one day getting a response. In October 2017, the METI organization sent a message to Luyten b in hopes of making contact with a potential extraterrestrial civilization. These, if they receive and understand our message, could respond by 2042. The message that has been sent is at the same time musical, mathematical, and scientific, and it is coded in radio waves to maximize its chances of being understood by an advanced extraterrestrial civilization. The METI organization was contacted by the Sonar Festival of Barcelona, a music and technology festival, to develop a message that would be sent into the cosmos to celebrate the 25th anniversary of the festival. The signal was named Sonar Calling GJ273b. It was sent from the ISCAT transmitter in Tromsø, Norway, over 3 successive days in October 2017. Among other things, it contains a tutorial on basic math and science, explaining physical concepts specific to our civilization, such as radio frequencies or our conception of time. In a way, a practical manual so that the aliens can understand the musical message and respond to us with the same communication process. In addition to the tutorial, the message includes 6 original pieces of music, commissioned by the Sonar Festival, short 10-second pieces of music. You may wonder why the Sonar Festival chose the planet Luyten b, and not, for example, Proxima b, whose habitability is still in question, and which is closer to us? Simply because the star of Luyten is visible from the northern hemisphere, where the transmitter is located. It is therefore more convenient to communicate effectively with potential extraterrestrials. We have now arrived at our destination, about 14 light-years from Earth. You are looking at the Wolf 1061 star system. Before we continue our exploration of the nearest habitable exoplanets to Earth, you need to understand why astronomers are looking for alien life on these exoplanets, and how they go about determining whether or not a particular exoplanet might harbor life. Why are we looking for life on exoplanets when it is very likely that we will never be able to communicate with the life forms that will have been discovered? You may be asking yourself this question, which is quite sensible, because even if a giant telescope allows us to find life on an exoplanet located several tens of light years away, several things could prevent us from entering into communication with this life. These are the same reasons that are given in response to the Fermi paradox, the paradox that wonders why, if there is life elsewhere than on Earth, extraterrestrials have never manifested themselves. First of all, it is possible that this life is microbial, aquatic, or animal, and that it does not understand us. And even if an advanced extraterrestrial civilization is found, its communication processes will be so different from ours that communication may be impossible. It is also possible that intelligent civilizations have existed, but that they did not last long on the scale of the universe. They would have quickly self-destructed because of technology, a nuclear war, or other. Or they have already tried to communicate with us, but we did not understand their signs, because their communication techniques are still too advanced for us. We can imagine dozens of answers to the Fermi paradox. But all we know is that the presence of extraterrestrial life elsewhere in the universe is not yet certain, and that perhaps the Earth is an exception. We also know that if another form of life is found elsewhere in the universe, it is very unlikely to come across another civilization that is as advanced as ours. So why are we looking for life on exoplanets? Not only to make contact with extraterrestrials, but also to better understand the appearance of life on Earth, and to find out if Earth is an exception. Currently, the Earth is an exception in the universe because it is the only known planet that hosts life. But perhaps our place in the universe is not so exceptional. Scientists are also interested in the question of whether life could exist in other forms. The life we know is based on 6 atoms: hydrogen, oxygen, carbon, potassium, nitrogen, and phosphorus. We have not yet observed other types of life, but that does not mean it is unlikely. This is the subject of exobiology, a discipline that imagines what living things based on elements different from ours might look like, using notions of astrophysics, planetology, biology, and chemistry. To find life on exoplanets, astrophysicists will proceed step by step. First, the idea is to detect an exoplanet by the transit method, or by radial velocity. The transit method is the most used method to detect exoplanets, but it has some limitations. The exoplanet HD 209458b, located 159 light-years away, was the first exoplanet to be discovered with this method. When a planet passes in front of its star, which is called transit, we observe a decrease in the luminosity of the star. This decrease in brightness of a few percent is measurable by photometry. The transit method allows us to deduce certain characteristics of an exoplanet, its period of revolution, its radius, and even, with precise instruments like the James Webb, certain elements present in its atmosphere. But this method has its limits. The planet must pass in front of its star to be detected, an event that is actually quite rare on the scale of the universe. For example, to see Venus pass in front of the Sun, we would have to wait a century. Once astronomers have detected an exoplanet, whatever the method used, they will deduce its characteristics to be able to establish if the planet is in the habitability zone of its star. This is called Goldilocks. The goal is to know if the planet can contain water in a liquid state, which is essential for the development of life as we know it. A planet too close to its star would be too hot, and the water would evaporate, and conversely, a planet too far from its star would be too cold, and the water would freeze. The balance is tenuous. You now understand why, while more than 5,000 exoplanets have been discovered to date, scientists are not yet certain that other forms of life exist elsewhere than on Earth. But being in the habitability zone of its star does not necessarily make the planet habitable. We have a good example in our solar system with Venus, often called the twin sister of the Earth. Astronomers say that until 715 million years ago, Venus was quite habitable, with large oceans like on the primitive Earth. In fact, Venus is very similar to Earth, with a similar mass and size, so it makes sense that they would have been similar in their early existence. But today, Venus is uninhabitable, with an average surface temperature of about 450 degrees Celsius, or 842 degrees Fahrenheit, and sulfuric acid rain. 715 million years ago, something caused a massive injection of carbon dioxide into Venus's atmosphere, creating an uncontrolled greenhouse effect that has resulted in the planet's hellish environment today. The profile of a habitable planet would therefore finally be quite similar to that of Earth, a rocky planet with an atmosphere neither too small nor too massive. These characteristics are modulated according to the type of star and the distance between the star and the planet. To confirm whether a planet is habitable or not, astrophysicists will not rely solely on its distance from its star or its surface temperature. They will look for biosignatures, in particular, photosynthetic biosignatures, which the largest telescopes today can detect. Now that you know how astrophysicists determine whether or not an exoplanet is habitable, and why they are constantly searching for an Earth-like habitable planet, we can begin to explore the Wolf 1061 system and its planet, Wolf 1061c. The Wolf 1061 star system is organized around the red dwarf, Wolf 1061, located about 14 light-years from us in the zodiacal constellation of Serpentarius. This star is also known as HIP 80824 and V2306 Ophiuchi. For the record, red dwarfs have the ability to burn up to 400 to 500 billion years, 40 to 50 times longer than our Sun. Around this red dwarf orbits at least 3 telluric planets. Wolf 1061c is the one we are interested in today because it is classified as a super-Earth and is located in the habitable zone of the star Wolf 1061. The star Wolf 1061 was first catalogued in 1919 by the German astronomer Max Wolf. This astronomer had published a list of faint stars that had a high proper motion. The proper motion is the apparent motion of the stars on the sky, as seen from the Earth. Later, the star Wolf 1061 attracted the interest of astronomers for its relative proximity to the Earth. Using the radial velocity method, astronomers discovered a triple planetary system consisting of 3 planets, Wolf 1061, B, C, and D. The habitable zone of the star Wolf 1061 is estimated to be between 0.1 and 0.2 astronomical units from the star. The planetary system of Wolf 1061 consists of 3 known planets. It is not excluded that there are others. These planets were detected by analyzing 10 years of observations of the Wolf 1061 system by the HARP spectrograph at the La Silla Observatory in Chile. The team of astronomers behind the discovery used radial velocity measurements of the star's spectrum to highlight these 3 exoplanets and their orbital periods. Wolf 1061b orbits the star in only 5 days, while Wolf 1061c takes 17.9 days to circle the star, and Wolf 1061d, further out, orbits in 217 days. The mass of Wolf 1061c is estimated to be at least 4.3 times that of the Earth, making it a super-Earth. The mass of Wolf 1061b is closer to that of the Earth because it is estimated to be at least 1.4 times that of the Earth, while the most distant planet is 5.2 times the mass of our planet. The 3 exoplanets of the Wolf 1061 system have masses low enough to be rocky planets, but this remains a supposition since we know neither their size nor their density. If this were the case, they would probably have a solid surface. To be able to determine these characteristics and to know more about the planets of Wolf 1061, it would be necessary to use the transit method. Even if for the moment no transit has been observed from Earth, astronomers do not give up hope of seeing a transit because the 3 exoplanets have short orbital periods. The chances of seeing a transit are 14% for planet B, 6% for planet C, and 3% for planet D, according to the team of astronomers from the University of New South Wales in Australia. Of the 3 exoplanets in Wolf 1061, only planet C is considered potentially habitable. Wolf 1061b is too close to its star, and Wolf 1061d is located at the outer limit of the habitable zone. Its habitability remains probable because everything depends on its own characteristics, which could not be observed. But while waiting to know more, it is the middle planet, Wolf 1061c, that interests astronomers. Wolf 1061c has long been considered the closest potentially habitable exoplanet. After the discovery of exoplanets closer to our solar system, it is part of the growing list of the closest potentially habitable exoplanets, along with Proxima Centauri b, Ross 128b, and Luyten b. It is, after Proxima Centauri b, the second potentially habitable planet in a triple planetary system. Wolf 1061c is a super-Earth located near the inner limit of the habitable zone of Wolf 1061. The habitable zone of the red dwarf has been estimated by astronomers to be between 0.11 and 0.21 astronomical units, or at most between 0.09 and 0.23 astronomical units. Wolf 1061c is located at 0.08 astronomical units from its star, thus at the lower limit of the habitable zone. It is called a super-Earth because its radius has been estimated to be more than 1.5 times that of the Earth. Its mass is 4.3 times that of the Earth, and its surface gravity is estimated to be 1.6 times that of the Earth. All these estimates have allowed astronomers to assume that Wolf 1061d should have a density close to or greater than that of the Earth. Other characteristics of Wolf 1061c could be estimated from the astronomers' observations. Its orbital period is 17.9 Earth days, and its equilibrium temperature is about -50 degrees Celsius or -58 degrees Fahrenheit, slightly higher than the equilibrium temperature of Mars. Wolf 1061c receives less than 1% of the Sun's luminosity. All these characteristics are only guesses at the moment, because the observation of Wolf 1061c was made with the radial velocity method. To know more, and to confirm the estimates of the astrophysicists, it would be necessary to observe a planetary transit. The method of transits would give us a more certain estimate of the radius, and thus of the density of the planet. We could then know if Wolf 1061c is an ocean planet or not. Because it is very close to its star, Wolf 1061c is certainly in synchronous rotation. As we saw at the beginning of this journey with the exoplanet Proxima Centauri b, it is indeed very likely that there is a tidal effect that makes the planet turn on its axis at each revolution around the star. This tidal effect would be explained by its proximity to its star, Wolf 1061. The planet Wolf 1061c would therefore always present the same face to its star, and could therefore harbor life only in the zone of separation between the diurnal face and the nocturnal face. This fictitious line between the illuminated zone and the zone perpetually plunged into darkness is called terminator. Unless the atmosphere of Wolf 1061c is thick enough for there to be a heat transfer from the day hemisphere to the night hemisphere. If Wolf 1061c were in our solar system, it would be too hot to harbor life because of its proximity to its star. But Wolf 1061, which is a red dwarf, is much cooler than our Sun. For comparison, its surface temperature is about 3,030 degrees Celsius, or 5,480 degrees Fahrenheit, while the surface temperature of our Sun is around 5,530 degrees Celsius, or 10,000 degrees Fahrenheit. Wolf 1061c is therefore well and truly in the habitable zone of its solar system. But to know if Wolf 1061c harbors life, it would be necessary to study its atmosphere. Being in the habitable zone is not enough for life to develop on a planet. As we have seen, the example of Venus is enough to understand that a planet can be rocky like Earth and located in the habitable zone of its star, but have characteristics that make life impossible. Astronomers have estimated that life could have developed on Venus for about 3 billion years because the planet's climate was then stable and temperate like Earth's, between 20 and 50 degrees Celsius, or 68 and 122 degrees Fahrenheit. But about 700 to 750 million years ago, a cataclysmic event caused a massive release of carbon dioxide into Venus's atmosphere, a gas that had previously been trapped in the planet's rocks. Some researchers believe that this event resulted from the strong volcanic activity of Venus. The result? An intense greenhouse effect and rising temperatures that have reshaped 80% of Venus's surface. Today, the planet that was considered as the twin planet of the Earth has an average surface temperature of 450 degrees Celsius, or 842 degrees Fahrenheit, and is considered as the hottest planet in our solar system. Venus was the victim of a runaway greenhouse effect. Heat became trapped in the atmosphere, and the planet became too hot for any form of life. Researchers estimate that during the 3 billion years that the planet was habitable, its landscape strongly resembled those of the primitive Earth, with lakes and oceans. These oceans eventually evaporated because of the heat, which only increased the surface temperature of Venus, since water vapor is a real heat trap. A vicious circle that has shaped the planet we know today, often referred to as an iron planet. In the same way as Venus, if the atmosphere of Wolf 1061c is rich in greenhouse gases, it could be too hot for it to be habitable, even if it is rocky, with characteristics close to those of the Earth, and is located in the habitable zone of its star. Stephen Kane, an astronomer specializing in exoplanets at San Francisco State University, and his team have studied the question of the habitability of Wolf 1061c. According to them, the climate of this exoplanet is rather chaotic. On Earth, climatic changes occur at a rather slow pace, since the Earth's orbit lasts 365 days. But on Wolf 1061c, which orbits its star in only 18 days, these climatic variations would be much faster. The frequency of freezing or warming would therefore be very fast. Imagine living on a planet where it is successively very hot and very cold, without transition. That said, astronomers are still waiting for more data on the planet's atmosphere to be able to make a statement. It is possible that the very short periods of freezing are sufficient to cool the planet, but it would be necessary to push the observations even further to confirm one of these hypotheses. Moreover, according to Stephen Kane and his team, because it is located very close to its star, it would be quite possible that Wolf 1061c, like Venus, experiences an uncontrolled greenhouse effect. There is, however, another argument in favor of the planet's habitability. Like Ross 128, the star Wolf 1061 is particularly quiet for a red dwarf. Most red dwarfs are very active and are prone to superflares that would destroy any life on nearby planets. Especially since red dwarfs are cooler than yellow dwarfs like our Sun, planets orbiting red dwarfs are located much closer to their star than the planets in our solar system. Scientists are not yet sure that Wolf 1061c harbors life. We have too little information to say with certainty that this exoplanet relatively close to our Earth is a paradise, a hell, or something in between. Let's assume that Wolf 1061c is potentially habitable. So what would life be like on this exoplanet, 14 light-years away from our solar system? Many researchers claim that humans could not live on this planet. It's true that planets within a star's famous habitability zone are likely to contain liquid water, one of the prerequisites for the development of an advanced civilization like ours. But researchers believe that in the case of Wolf 1061c, the development of life similar to the one we know would be very complicated. The living conditions for humans would not be pleasant, with a gravity 1.6 times greater than that of the Earth. In addition, its synchronous rotation implies that there is a side of the planet perpetually plunged in the dark, with very low temperatures, and another side without ever nights, with very high temperatures. Humans might be able to survive in the middle zone, the terminator, but they would not live comfortably there. And it is unlikely that in these conditions a species similar to ours, the result of evolution and adaptation to our terrestrial environment, would have been born. But this does not exclude other types of animal or plant species. The question that also arises is that of the conditions of life on a planet orbiting a red dwarf. The synchronous rotation and its two opposite hemispheres are not the only obstacles to the development of a species, such as man on the planet Wolf 1061c. Living next to a red dwarf is not easy. These stars are known for their frequent eruptions, which emit UV and X-rays, dangerous for human life, and for that matter for all forms of life. The surroundings of a red dwarf star are therefore not a very hospitable environment. Yellow dwarfs like our Sun can have outbursts of anger, like red dwarfs. But in addition to being less frequent, they are less dangerous because the planets orbiting a yellow dwarf are more distant than those orbiting a red dwarf. The Earth is far enough from the Sun not to fear possible eruptions, and we are protected by the magnetic field and by our atmosphere. Planets orbiting red dwarfs are too close, and even if they have an atmosphere, it can be torn apart by the onslaught of stellar flares. Scientists believe that there is a cumulative effect. That is, the more flares there are, the more the atmosphere is torn apart, regardless of the violence of the flares. So yes, recent studies have found that red dwarf eruptions are not as energetic as has been thought for years. Researchers may have overestimated the violence of red dwarf flares, but if the cumulative effect exists, it is the frequency and not the violence of the eruptions that is dangerous. However, not all astronomers are pessimistic about the possibility of life developing in the orbit of a red dwarf. Red dwarfs represent 3/4 of the stars in the Milky Way, and we have already discovered many that are surrounded by rocky Earth-like planets. What would be strange is that among all these planets, which are so many possibilities for the emergence of life, there is not a single form of life that is developed. Other factors may affect the habitability of a planet located near a red dwarf. The characteristics of its atmosphere, its thickness, its liquid water content, the interactions between the magnetosphere and the ionosphere with stellar winds. If the right factors are present, an exoplanet of a planetary system organized around a red dwarf could be habitable by creatures other than humans who would resist other conditions. Moreover, the case of Wolf 1061c is promising, since Wolf 1061 remains a rather quiet red dwarf, with relatively low power and infrequent eruptions. Suppose there were life on the planet Wolf 1061c. The conditions for life would be very different from those on Earth. Imagine a world where there are only days or only nights, depending on where you are. The years would also be shorter, since Wolf 1061c orbits around its star in only 18 days. A year would last barely 3 Earth weeks. Because Wolf 1061c orbits a red dwarf and not, like the Earth, a yellow dwarf, the landscapes would also be very different, as well as the luminosity of the planet. Our Sun emits yellow radiation, but red dwarfs emit a reddish radiation. the inhabitants of Wolf 1061c would still have a red star above their heads, and the stellar disk would be larger than that of the Sun, since the red dwarf is closer to Wolf 1061c than the Sun is to the Earth. It is possible that there are plants on Wolf 1061c because plants have a photoreceptor for red light, phytochrome, a blue-green pigment found in plant cells. However, the plants on Wolf 1061c would be very different from terrestrial plants, whether in terms of flavor, smell, or appearance. They would probably be black to better absorb the red light emitted by the star. You may find it difficult to imagine a flourishing life but limited to a small strip in the middle of the planet. This is normal. This representation is very far from what we know. But the good news is that if there is life on Wolf 1061c, it is not necessarily limited to the terminator if the atmosphere has the right characteristics. For a very long time, astronomers believed that life on synchronously rotating planets was only possible in the terminator zone. They also thought that for heat transfer to be efficient enough from the day side to the night side, the atmosphere would have to be so thick that it would prevent photosynthesis. It was also thought that such planets would experience high winds and torrential rains all the time, making any complex life forms unlikely. Here is what life looked like according to these assumptions. There are no humans, but plants can survive in such an environment. They can adapt to the constant winds, for example, by anchoring themselves in the ground with their roots, or by developing flexible and unbreakable leaves and branches. There are also animals which communicate by infrared rather than by cries and smells as on Earth, because storms make this type of communication impossible. Underwater life is protected from strong winds and eruptions by the water, and is supported by vast blooms of plankton and black photosynthetic algae. A plankton bloom is when phytoplankton multiply in an ocean. On Earth, this phenomenon has been demonstrated in the depths of the Arctic Ocean and under the sea ice in Antarctica. We can see it forming like a green sheet from space. This phenomenon can only occur if two elements are combined: nutrients and light from the star. We can therefore imagine that these forms of underwater life would develop in the oceans of the illuminated hemisphere of Wolf 1061c. Further studies were conducted from the late 20th century onwards with promising results. Astronomers are now a bit more optimistic about the emergence of life on this type of exoplanet. Studies conducted at the end of the 1990s by NASA researchers have shown that the atmosphere of a planet, if it does contain the greenhouse gases CO2 and H2O, only needs 100 millibars, or 10% of the Earth's atmosphere, for the heat of the star to be transported to the night side. This figure is reassuring because it shows that photosynthesis could then take place. Other studies have shown that in the night side, seawater can circulate efficiently without freezing if the ocean basins are deep enough for the water to circulate under the ice cap. In other words, one could very well find underwater life in a synchronously rotating ocean world, even on the night side. A 2010 study estimated that ocean temperatures would not fall below -33 degrees Celsius or -27 degrees Fahrenheit in the hemisphere perpetually immersed in night. For the difference between the day and night side to be minimal, there would have to be clouds. If Wolf 1061c has clouds, then astronomers agree that this greatly increases its chances of being habitable. Wolf 1061c could be an ocean planet. Maybe you have a hard time picturing what this type of planet looks like. Scientists describe them as a planet that would be covered with an ocean or water over its entire surface. The depth of this ocean could be several tens of kilometers, but this type of planet remains hypothetical. For the moment, we can only think about the hypothesis according to which Wolf 1061c would be entirely covered with water, without really any evidence to confirm or deny this hypothesis. If Wolf 1061c were an ocean planet, it would be covered with high-pressure and high-temperature oceans. To date, astronomers do not know if this environment would be conducive to biological chemistry. What we do know is that if the oceans of Wolf 1061c were to support life, it would certainly be different from the underwater life found in our terrestrial oceans. We know that the oceans are capable of wonders. The origin of life on Earth remains mysterious, but the most likely hypotheses agree that it was born in our oceans, or at least in water. Underwater life can survive extreme conditions. On Earth, we have found living organisms capable of developing in the Dead Sea. The tardigrade is the best example of an ultra-hardy species that can survive incredible pressure conditions. This 8-legged animal, which can grow to just over 1 millimeter, can withstand temperatures ranging from minus 273 degrees Celsius or minus 460 degrees Fahrenheit to plus 150 degrees Celsius or 300 degrees Fahrenheit, but also X-rays, to which it is 1,100 times more resistant than humans, and pressures 4 times greater than those of the deepest ocean. It can also resist to the lack of oxygen or to the isolation because it reproduces alone. It is cryptobiosis that allows it to be so resistant, a state in which it reduces its metabolic process to 0.01% of normal, so that it is almost dead but not quite. It can remain in this state for decades and rehydrate to wake up at any time. It is therefore quite possible that living organisms of this type can be found on planets like Wolf 1061c, where conditions are less mild than on Earth. There is still much to discover about the secrets of the exoplanet Wolf 1061c. There are many rocky planets in our galaxy, but some of them are located tens or hundreds of light years away from us. Wolf 1061c is one of the most promising because it is close to Earth. The next step to establish an ever more precise portrait of this promising exoplanet is to observe its transit. The transit method will provide crucial information to better understand this planet and determine if it may contain life. When Wolf 1061c passes in front of its star, it will cause a decrease in brightness at Wolf 1061. Scientists will then be able to analyze this difference in brightness to deduce the composition of its atmosphere. The higher the orbital period of an exoplanet, the more difficult it is to apply the transit method, because transits are rarer. In the case of Wolf 1061c, the orbital period is short, which suggests that a transit will be observed rather quickly. Moreover, when the transit method is applied to discover an exoplanet, it is necessary to have observed several transits to conclude that there is a planet in orbit around the observed star. The transit method provides information such as the radius and density of the exoplanet. Astronomers know the spectrum of the star, so they can derive the value of its radius. The relative decrease in the luminosity of the star during the transit is equal to the square of the ratio of the radius of the exoplanet to that of its star. This calculation allows to obtain the radius of the exoplanet. By confronting the radius to the mass, we then deduce the average density. The transit method also provides information on the chemical composition of the planet's atmosphere, as well as its temperature. To do this, astrophysicists measure the spectrum of the star without transit, then with, to deduce the spectrum of the exoplanet. The James Webb Telescope, which was launched in December 2021, will greatly help scientists learn more about Wolf 1061c, its unique characteristics, and whether or not it harbors life. The Space Telescope carries several instruments that allow it to see in the near and mid-infrared. Moreover, in August 2022, the scientific community announced that James Webb had detected the presence of CO2 in the atmosphere of an exoplanet for the first time. This exoplanet is WASP-39b, a gas giant the size of Saturn. It was one of the first exoplanets examined by James Webb from July 2022, and there is no doubt that Wolf 1061c is on the waiting list. Even more impressive, the telescope was able to detect, in addition to CO2 water vapor, carbon monoxide, sodium, potassium, and sulfur dioxide. The detection of this last compound has highlighted a photochemical phenomenon observed for the first time on an exoplanet. The James Webb Telescope is not the only one to be promising. The extremely large telescope of ESO, the European Southern Observatory, should be completed and put into service in 2028. This telescope, currently under construction in the Atacama Desert in Chile, will be the largest ground-based telescope ever built, with a main mirror 39 meters in diameter. For comparison, the James Webb Telescope orbiting the Sun, 1.5 million kilometers or 930,000 miles from Earth, has a mirror 6.5 meters or 21 feet in diameter. The European Southern Observatory's Very Large Telescope has already demonstrated its capabilities by discovering barium in the atmosphere of the exoplanets WASP-76b and WASP-121b in October 2022, the heaviest element ever found in the atmosphere of an exoplanet. So, imagine what the ELT's capabilities will be. This super powerful telescope, when completed, will stand 3,000 meters or 10,000 feet above the Earth and will capture 100 million times more light than the human eye. If our universe is about 14 billion years old, you should know that our Milky Way was born almost at the same time. Indeed, scientific research has allowed us to estimate its age by observing the oldest bodies in it. This is the case of the star HE 1523-0901, one of the oldest in our galaxy. Aged 13.2 billion years, this red giant is located at 7,500 light-years from Earth. This news surprised scientists, including the astronomer Anna Frebel and her team, who discovered it in 2007. However, only 6 years later, it was the turn of the star HD 140283 to steal the show. Estimates do not allow to know precisely what is its age. Measurements made with the Hubble satellite led to the conclusion that it could be 14.5 billion years old, which is more than the observable universe. But taking into account the uncertainty of the results and the new measurements bring this estimate between 13.2 and 13.7 billion years. Another fascinating discovery concerning HD 140283 comes to question its origin. In view of its high rotation speed and its location, researchers have put forward a hypothesis. It could be that the star was not formed in the Milky Way, but that it was born in a dwarf galaxy nearby. This dwarf galaxy in question would then have collided with ours to end up devoured, thus offering us part of the stars it housed. However, HD 140283 is no longer the oldest star observed to date. This title belongs to a supermassive star born only 600 million years after the Big Bang. Its name being too complex to be mentioned, astronomers refer to it as the Methuselah star. Located only 200 light-years from our solar system, it is the oldest star we have ever seen. The chances of finding it were slim, but this feat was possible thanks to the pictures taken by the SkyMapper telescope. To estimate its age, scientists based themselves on its iron abundance. Indeed, the telltale sign that the star is so old is the complete absence of any detectable level of iron in the spectrum of the star. Indeed, it took a few million years after the Big Bang for heavier elements such as iron to form in the core of the first stars. The explosion of these stars and supernovae allowed the diffusion of new atoms everywhere in the universe. Thanks to this discovery, we know that the Milky Way is almost as old as the cosmos itself. In the almost 14 billion years of its existence, billions of stars have been born and died in it. The effect of its gravitational force has allowed the creation of complex solar and planetary systems such as ours, systems much closer than we could have hoped. This is the case of Proxima of the Centaurus. If this name rings a bell, it is not without reason. Indeed, Proxima Centauri is the closest star to our Sun ever discovered. But beware, with the technologies we currently have, it is impossible for us to reach it. Let's imagine that you are driving a space shuttle going at a speed of 100 kilometers per hour or 60 miles per hour. To get to Proxima, you would need 60 million years. Now, if you had the possibility to travel at the speed of light, the travel time would be more acceptable, a little more than 4 years only. Located at almost 4.2 light-years from the Sun, it is a small and not very luminous star compared to ours. Proxima is about 8 times less massive and 20,000 times less bright than the Sun. As for its size, it is estimated to be 7 times smaller. It belongs to the category of red dwarfs. Red dwarfs are the most common stars in our galaxy. They represent about 80% of the stars in our galaxy, a total of 240 billion out of the 300 billion stars in our Milky Way galaxy. Even more surprisingly, searches for exoplanets near our own have revealed that 3 relatively massive bodies orbit our small neighbor. These planets are respectively named Proxima B, C, and D. Unfortunately, these new worlds do not seem to be ideal candidates for the emergence of life as we know it. Due to its strong and unstable magnetic field, solar flares are frequent on Proxima Centauri. Thus, although Proxima b is located in the habitable zone of its star, the chances of it harboring life forms remain slim. Another surprising feature of Proxima Centauri is its relationship with 2 other nearby stars. These double stars are called Alpha Centauri A and B, and together with Proxima, Alpha Centauri C, they form an unusual star system. Not far from Earth, there are other planetary systems just as incredible, fueling beliefs of extraterrestrial life. If you're a science fiction fan, you may be familiar with the series Babylon 5. In this show, the eponymous space station is located in the Epsilon Idani system. But this system was not invented for the purposes of the script. It does exist. Located at 10.5 light-years from us, the orange dwarf in its center is the 10th closest star to us. More massive and bright than red dwarfs, these stars remain less imposing than yellow dwarfs such as our Sun. According to astronomers' estimates, the star is 800 million years old. It is therefore a newborn among the wonders of the cosmos. This star gives us a glimpse of what our Sun was like after only a few million years of existence. But that's not all. After observation, astronomers have revealed the existence of a remarkable exoplanet. A gas giant, 1.5 times more massive than our Jupiter, and located at about 3.5 astronomical units from its star. That is, 3.5 times further away than the Earth is from the Sun. Between the star and its planet is a belt of dust, asteroids, and other cosmic debris. The same is true outside the planet's orbit. This second belt would shelter colder bodies such as comets. This particular arrangement is not unlike that of our own solar system. Between Mars and Jupiter is a ring of low-mass bodies called the asteroid belt. And outside the orbit of Neptune, we find the famous Kuiper belt, populated by comets. If the Epsilon Idani system interests scientists so much, it is because it gives us a good overview of what our solar system may have been at the beginning of its formation. Currently, research continues in order to detect other planets that have escaped the measurements of astronomers. If our Milky Way is home to many red dwarfs, orange dwarfs, and other yellow dwarfs, it also has much more impressive stars. Bodies with phenomenal dimensions, constantly growing, until they swallow the planets that have the misfortune to be near them. These stars are called red giants. Some are visible from Earth, and are sometimes the source of myths about constellations. This is the case of Arcturus. Observable from the northern hemisphere of our globe, it is the brightest star in the constellation of the Cattleman. If its mass is equivalent to that of the Sun, its luminosity is 300 times greater. But how did Arcturus get there? Well, the star has consumed all the hydrogen contained in its center to attack the outer layers. It is then that nuclear fusion reactions started, consuming helium for the synthesis of heavier elements. Because of these reactions, the star has gained in volume, but it has lost in density and temperature. Since then, its radiation tends towards the red, hence its name. At the end of the combustion process, the red giant will give way to a huge cloud of gas with a white dwarf at its center. You know these clouds as planetary nebulae. You should know that a similar fate awaits our Sun in about 4 to 5 billion years. By observing our sky, astronomers have counted more than 1,000 white dwarfs in our galaxy. But some estimates suggest that there are several tens of billions. Let's get back to Arcturus. In addition to its enormous size, this star is intriguing because of its orbit. located in the so-called Milky Way halo, it moves on a very inclined plane, unlike most other stars. It is therefore not centered on the disk of the Milky Way like our Sun. At present, we know that about 30 stars orbit on this particular plane. Together they form the Arcturus group. One reason for this unusual behavior is that the stars in this group are believed to have come from another galaxy that collided with ours 5 billion years ago. In any case, Arcturus will no longer be visible to the naked eye within a few 100,000 years. If Arcturus is a big star, it is nothing compared to VY Canis Majoris, a red hypergiant located in the constellation of Canis Major, about 3,900 light-years from Earth. It is considered one of the largest known stars in the observable universe, but it is also the largest star in our galaxy. The latest estimates indicate a monstrous size, 2,200 times that of our Sun. If it took the place of our Sun in our solar system, it would extend between the orbits of Jupiter and Saturn. Next to it, our Sun, so huge in our eyes, would be only a speck of dust. VY Canis Majoris is also very bright. It emits about 400,000 times more light than the Sun. However, even giants are not eternal, and this hypermassive star is dying, little by little. Being very unstable, it loses huge amounts of matter, second after second. Thus, its lifespan should not exceed more than 1 million years. Within 100,000 years, VY Canis Majoris will explode into a gigantic supernova. Yes, VY Canis Majoris has a terrifying scale. But lurking in the cosmos, even more massive stars radiate throughout the observable universe. Such is the case with R136A1, a massive star located in the Tarantula Nebula. In this region of the cosmos, stars grow like mushrooms on the edge of country roads. This star nursery is located in the Large Magellanic Cloud, a dwarf galaxy very close to the Milky Way, behind the Great Dog and Sagittarius. Just as the Moon is a satellite of the Earth, we can say that these galaxy embryos are satellites of our Milky Way. R136A1 is thus to date the most massive star known in our universe. Its mass is estimated at 230 times that of the Sun, also emitting 5 million times more light. Thus, if we were to compare our Sun to this star, it would not be brighter than the full moon. This unprecedented brightness indicates that the star is losing mind-boggling amounts of matter at every moment. Thus, taking this data in reverse, it is estimated that R136A1 must have weighed at its birth 320 times the mass of the Sun. A record as fascinating as terrifying, breaking our beliefs about the maximum size of stars at the time of its discovery. But like VY Canis Majoris, its lifespan will be short. This giant among giants will probably not shine for more than 4 million years. On the scale of the universe, this represents only a blink of an eye. When it reaches the end of its life, it could explode in a cosmic fireworks display of enormous proportions, a supernova. Fortunately, hypermassive stars are few and far between in our galaxy. However, there are celestial objects even rarer and more dangerous than these molten giants. objects so massive that nothing can escape, neither matter nor light. These are, of course, black holes. It has been known for several years that most galaxies have a hypermassive black hole in their center. Ours is no exception. In 2002, a group of astronomers used high-resolution observations made with the Keck telescope and the VLT to detect this cosmic abyss. By observing the motion of stars in the center of our galaxy, they found that some of them were undergoing abnormal accelerations. This could only mean one thing: an invisible object with an incredible force of gravity must be nearby. This discovery was a direct proof of the existence of supermassive black holes. The hypothesis had already been formulated by Albert Einstein at the beginning of the 20th century, following his work on relativity. However, the Austrian genius did not believe in the existence of such objects. To understand how Einstein's theories predicted the existence of black holes, we need to look at a physical datum called libration velocity. This value tells us how fast a body must travel to get out of the gravitational field of a star whose mass and radius are known. By pushing the reasoning, we understand that for a star of extreme density, the libration speed is higher than the speed of light. However, the theory of general relativity tells us that this speed is a universal constant and that nothing can exceed it. It is therefore assumed that for a star with a very small radius compared to its mass, it would be able to swallow light. This is how the hypothesis of black holes was put forward. Today, their existence is accepted, and research continues to decipher their mysteries. Indeed, our current understanding of black holes is limited. We know that these celestial objects are extremely massive and compact. Their gravitational force is so strong that nothing, not even photons, can resist their attraction. Some of them are formed when supermassive stars die. The heart of the latter collapses on itself in a cataclysmic event, bringing into play prodigious forces. This is how stellar black holes come into existence. But stellar black holes, although impressive, pale in comparison to their cousins. If the mass of a stellar black hole, born in the ashes of a star, can reach 10 to 20 times that of the Sun, it is nothing compared to the 40 billion solar masses that supermassive black holes can have. Sagittarius A, located 27,000 light-years from Earth, is the black hole at the center of our galaxy. With a mass of about 4 million times that of the Sun, our star appears tiny. And yet, next to these monsters of the cosmos, even our galactic black hole, although immense, can hardly compete. M87, of its name, would have a mass equivalent to 6.5 billion times that of the Sun. Thus, M87 would have a mass 600 times greater than Sagittarius A. But how did these giants that inhabit the middle of most galaxies come into existence? This question is very much debated by the scientific community at the moment. Some believe that they were originally stellar black holes that evolved by accretion of matter over several billion years. However, many researchers reject this hypothesis. For this, they argue that there is not enough matter available near the black holes to ensure such expansion. Thus, others believe that these chasms were formed during the first moments of our universe, when it was much hotter and denser. perhaps we will know more in the next few years. Another fascinating thing about black holes is what is called the event horizon. This is a region around the black hole from which gravity is so strong that it becomes impossible to escape its attraction. This boundary thus separates the observable world from the heart of the abyss, allowing us only to make assumptions about its nature. It is not a physical limit, like a wall or a barrier, but a zone of space from which everything that falls inside is ineluctably swallowed up. Beyond this point, the laws of physics as described by the theory of relativity no longer apply. However, if you were able to pass the event horizon and survive your journey, it is likely that your body would undergo a phenomenon of spaghettification. This strange term designates a phenomenon that is much less so. On Earth, gravity is strong enough to hold us down. However, it is not strong enough for a difference in attraction to be felt between our head and our feet. However, this is precisely what would happen if you were to get too close to a black hole. The simple distance between your upper and lower body would be strong enough to stretch your body like a long string. Moreover, at the horizon of the black hole, it is considered that space and time become infinite. One of the feats of the genius Albert Einstein is to have demonstrated that space, like time, are nested dimensions that can be bent. Thus, the incredible density of black holes bends space and dilates time in a spectacular way. As you move closer to their center, you would see time passing slower and slower until it almost stops at the horizon. It is difficult to imagine what lies at the heart of them. Our current understanding of things leads us to think that a singularity is hidden there. This singularity designates a point of infinite density, causing a curvature of space-time, also infinite. As you can imagine, this image does not please scientists. They are therefore trying to unravel the mystery of the heart of black holes by appealing to the various theories of quantum mechanics. Unfortunately, no satisfactory conclusion has been found so far. Nevertheless, our observations of black holes have revealed something quite surprising. We were just explaining that nothing, not even light, can escape from a black hole. Light is an electromagnetic wave, so black holes cannot emit radiation. And yet, a genius scientist managed to demonstrate the opposite in 1974. His name is Stephen Hawking. He proved that black holes do emit radiation, and that this is an integral part of their nature. Although this radiation is undetectable with the current means, because extremely weak, several experiments confirm its existence. To explain this paradox, we must once again turn to quantum mechanics. Thanks to it, Hawking was able to demonstrate that black holes do emit a radiation, now called Hawking's radiation. This is a thermal radiation caused by quantum fluctuations in the space-time around the black hole. These variations would lead to the creation of virtual particles separated into two groups. The first part would be absorbed by the black hole, while the other would escape from it, thus generating the famous radiation. If black holes have not yet revealed all their mysteries, they nevertheless remain objects of fascination that are conducive to the emergence of many theories. Interdimensional portals, origin of the Big Bang, glass holes, gateway to the multiverse. One thing is sure, these spatial abysses have not finished making talk about them. Our galaxy is home to many things that arouse our curiosity. It alone contains between 200 and 400 billion stars, but also between 100 and 200 billion exoplanets. So we are still in the early stages of discovery. Nevertheless, we also know that the Milky Way is only a drop of water in an ocean of other galaxies of various sizes and shapes. The observable universe would contain 2,000 billion of them. This inordinate number is enough to make one dizzy. And yet, the observable universe would represent only a dust. Indeed, the entire universe could contain 13 million times the observable universe. With so many bodies in the universe, it would be logical to think that at least one of them would contain a form of life, such as it exists on Earth. Some even believe that life could be much more diverse than we can imagine. It is possible that within our own galaxy, there are tens of thousands of planetary systems with primitive and complex life forms, extraterrestrials with reason, capable of thinking and interacting in complex societies. Unfortunately, there is no direct evidence that life exists anywhere but on Earth. But if life is potentially so abundant in the cosmos, how can we explain that we have never come across at least one living creature outside our planet? This question, which obsesses astrobiologists as much as amateur astronomers, is known as Fermi's paradox. Enrico Fermi is an American physicist of Italian origin who, among other things, worked on nuclear physics during the first half of the 20th century. Winner of the Nobel Prize in Physics in 1938, he was also interested in the question of the number of planets in the universe. After making estimates, he concluded that the probability that we are the only life form in the universe was ridiculously low. He then asked the question: if there were extraterrestrial civilizations, their representatives should already be with us. Where are they then? This sums up Fermi's paradox quite well. In response to this question, many scientists have put forward hypotheses. One of the most commonly accepted is that the distances separating the planets of the same galaxy are such that it would be impossible to cover them. Even traveling at the speed of light, it would take too long, especially when we know that our galaxy is about 100,000 light-years in diameter. Others also put forward the problem that resources are too limited to colonize other planets by traveling through space. Even if we progressed by colonizing planets in succession, many of them would be too inhospitable or too poor in certain materials to serve as staging points for such an expansion. Finally, some think that a form of life capable of traveling rapidly from planet to planet would have no interest in coming to Earth to meet us. For these beings coming from elsewhere, we would not be more evolved than simple bacteria. But it is human nature to dream. Our thirst for knowledge feeds a burning desire to meet people from another world. Thus, even if the probability that the human species will one day encounter extraterrestrials is low, we will always look for their presence at the edge of the universe. If we haven't discovered alien counterparts despite all our research, there are stranger, but also more dangerous things that scientists have observed while scanning the cosmos. Terrifying discoveries, such as the existence of black holes and other phenomena of cataclysmic proportions. As explained earlier, the death of some massive stars can give rise to stellar black holes. But sometimes things happen differently, giving rise to a much more spectacular event, a supernova. Supernovae are very violent stellar explosions that occur at the end of the life of a massive star. There are two types, Type 1a supernovae and Type 2 supernovae. Type 1a supernovae occur when a neutron star accretes too much matter around it, often from a neighboring star. This gain of matter continues until it triggers a nuclear fusion chain reaction that causes the star to explode. These explosions are extremely bright and all give off about the same luminosity. This constant allows scientists to measure their distance quite accurately. Type 2 supernovae are formed when the core of a massive star collapses under its own weight, triggering an explosion that destroys the star. Type 2 supernovae are even more luminous than Type 1a supernovae, but the amount of light they give off varies considerably from one explosion to another. These cosmic booms are uniquely violent events. Fortunately, the chances that we will ever be affected by one of them are slim. Although they occur every 3 seconds in the observable universe, they are rarer in the Milky Way. It is estimated that the frequency is in the order of 1 to 3 every 100 years. It is also important to understand that under their destructive appearance, supernovae play a crucial role in the evolution of the universe. By expelling matter over incredible distances, they allow the propagation of heavy elements, thus serving for the creation of new stars and planets. As the astrophysicist Hubert Reeves said, "We are all stardust, because the atoms that make up our bodies and the world around us come from stars that died billions of years ago." For as long as we have known that supernovae exist, none have been observed in our Milky Way. However, such a phenomenon would have occurred near us in the year 1604. SN 1604, of its scientific name, is better known as Kepler's supernova. This one remained visible in the skies for more than a year before gradually disappearing. The German astronomer Johann Kepler thought he had just observed the appearance of a new star. He detailed this unprecedented phenomenon in a book entitled On the New Star in the Foot of Ophiuchus. Since then, no other explosion of this kind has been observed directly in our Milky Way. However, it is very likely that it has happened since. The second closest supernova that we have seen is called SN 1987A. Its light reached the Earth on February 23, 1987, and was observed only a few hours later by professional and amateur astronomers. It occurred in a nearby galaxy, the Large Magellanic Cloud, located more than 160,000 light-years away. According to recent analyses, it is probably a Type 2 supernova, produced by the death of a red supergiant. The study of the latter has allowed us to learn more about the death of stars and the way they propagate matter through the cosmos. Moreover, some elements from this explosion have reached us. This is the case of neutrinos, elementary subatomic particles of very low mass that hardly interact with matter. SN 1987 allowed us to prove their existence, advancing research on particle physics. Thus, even such distant events can inform our local understanding of the world. It is also fascinating to see how such a large explosion finally leads us to discoveries on the subatomic scale. Even if supernovae are very interesting, it is not recommended to get too close to them. Just like black holes, they bring into play considerable forces with disastrous consequences. For example, Type 2 supernovae, which are the most powerful but also the rarest, emit a luminosity equivalent to 10 billion times that of the Sun. To put it another way, the explosion of a single star can shine brighter than the entire galaxy that hosts it. This is notably the case of the supernova SN 1999 EM. Located 25 million light-years from Earth, its light in the visible range is currently equivalent to 200 million times that of the Sun. All this is impressive, even terrifying, but it is nothing compared to hypernovae. These particular explosions are hotter, brighter, and even more destructive. We speak of hypernova when the explosion is of the order of 100 supernovae. The power released is then 10 to the 46th power joules. The Tsar Bomba, the most powerful nuclear bomb ever exploded, only released 10 to the 17th power joules. It was therefore about 100,000 billion times less powerful. To put it another way, if our nuclear bombs had the force of a flick of the wrist, hypernovae would be as powerful as a kilo of TNT. In this very specific category of cosmic explosions, there is one that absolutely outclasses all others. It is the most powerful supernova ever detected. Its name is ASA-SSN-15LH. This is literally a cosmic assassin whose magnitude exceeds the limits of our imagination. The scientists behind its discovery explain that ASA-SSN-15LH is the most powerful supernova ever discovered in human history. The source of the power of the explosion and the energy released remains a mystery, since no theory of physics can really explain it. And for good reason. When the intensity of the explosion was at its peak, this hypernova shone 20 times brighter than all the stars in our galaxy combined. Faced with this discovery, scientists were left speechless. How could a phenomenon of such magnitude have occurred? And yet, they still managed to observe the hypernova, even though it is located 3.8 billion light-years away. All the analyses have come to the conclusion that the light spectrum of this formidable blast does not resemble at all that of other previously studied supernovae. In particular, they tell us that the original star must have been poor in hydrogen, which is not the case for most of the stars around us. One theory is that ASA-SSN-15LH is the consequence of the explosion of a particularly rare type of neutron star, a magnet star. Also called a magnetar, it would be a rotating star with a rotation speed of 1,000 revolutions per second, converting all the energy of its rotation into light. Other scientists put forward another theory to explain the extreme characteristics of ASA-SSN-15LH. It is known that most of the observed supernovae are found in faint and small galaxies. This is a sign of their genesis and intense activity. Stars form and die more quickly. The hypernova occurred in a galaxy even larger and more luminous than our Milky Way. The second hypothesis is that it is not a star explosion, but an unusual phenomenon near a black hole of extreme mass. In any case, the studies around this mystery continue. Let's hope that it will lead us to other fabulous discoveries in the years to come. If Type 2 supernovae are the result of the collapse of a massive star, Type 1a supernovae work differently. For these explosions to occur, the presence of a neutron star is necessary. But what exactly is a neutron star? In fact, neutron stars are very compact and dense celestial objects that form when massive stars end their life cycle. Lighter stars would become white dwarfs, while heavier stars could form stellar black holes. These giants would eventually collapse under their own gravity, causing an extreme compression of matter. This compression is such that the two elementary particles, protons and electrons, end up fusing to form neutrons. This nuclear fusion produces a lot of energy, which prevents the total collapse of the star, creating a stable neutron star. Neutron stars have diameters of a few kilometers, but a mass comparable to that of the Sun. If you could buy a 1-liter bottle containing the same volume of a neutron star, the mass of that bottle would be about 1,000 billion tons. That's about the weight of all the things produced by all of humanity. From clothes to packaging, roads, dots, and skyscrapers. This incredible density produces extremely strong gravitational fields, which can reach millions of times the Earth's gravity. It is also important to know that neutron stars are not very bright, at least in the visible spectrum, because they do emit light, but it is mainly X-rays and gamma rays. Like supernovae and black holes, there are several kinds of neutron stars. They are mainly grouped in two categories. On the one hand, we have pulsars, and on the other hand, neutron stars that produce gamma-ray bursts. The pulsars emit bursts of X-rays or gamma rays at regular intervals. We could compare them to a kind of cosmic sonar. Discovered for the first time in 1967 by Jocelyn Bell and Anthony Hewish, they have recently been used to demonstrate the existence of gravitational waves. A particular type of wave, and very difficult to detect, subjecting matter to the laws of gravitation. Their existence had been predicted by Einstein's relativity, but it was only proven in 2016, following the collision of a binary system of two black holes. This cosmic event of massive magnitude generated waves strong enough to be detected on Earth, despite the 1.3 billion light-years that separated them from us. It was also the first direct evidence of the existence of black holes. But let's get back to our pulsars. At present, we have been able to detect about 3,000 of them, mainly in our galaxy and in our close neighbors. The reason pulsars emit such regular waves is that these dense bodies rotate on themselves at an extreme speed. Their rotation period varies between a few milliseconds and a few seconds. This period of rotation is given to us by the nature of the waves they emit. Radio waves for the slowest, and X-rays or gamma rays for the fastest. As for pulsars producing gamma ray bursts, it is not one, but two bodies. These two pulsars orbit each other at high speed, forming a binary system. When they collide, they also create a wave of gravitational waves that can be detected from Earth. A gamma-ray burst is certainly one of the most violent phenomena that occur in the cosmos. Like supernovae, this shock generates a luminosity that can reach billions of times that of the Sun. Sometimes gamma-ray bursts are associated with very high-frequency radio waves. These are called FRBs. These are short-lived emissions of intense electromagnetic radiation of extragalactic origin. FRBs are considered to be very rare and enigmatic phenomena, with only about 100 events detected to date. During our journey, we have seen that the universe is full of intriguing objects. At any given moment, events of unprecedented power are taking place, and uncontrollable forces are at work. Black holes are a good example. If these objects, by their nature, are already mysterious, there is a particular type even stranger. They are called quasars. This is an acronym for quasi-stellar radio sources. They are celestial artifacts, very bright and very distant, which are found in the heart of some galaxies. These galaxies are called active because their center produces a luminosity that nothing, not even supernovae, equals in the cosmos. The most likely theory is that quasars result from a large accretion of matter around a supermassive black hole. Particles such as hydrogen or helium are thus strongly accelerated under the effect of gravitation. This high speed gives them such energy that they produce a strong electromagnetic radiation of a blinding brightness. Let's take the example of the quasar 3C273. Discovered with the help of photos taken by the famous Hubble telescope, it is located about 2.4 billion light-years from our galaxy. Its prodigious luminosity exceeds 1,000 billion times that of the Sun. This represents as much light as 1,000 times all the stars in our galaxy combined. Thus, 3C273 is one of the brightest objects ever observed. Today, probability calculations suggest that there are about 100 billion quasars in the cosmos. Since the quasars are all located at cosmological distances, i.e. several billion light-years, this tells us something about the nature of our own universe. Indeed, if the universe was static and unchanged since its creation, we should observe these prodigious sources of light near us. But this is not the case. The vast majority of them are located in the outer reaches of the observable universe. This discovery is therefore a strong argument in favor of the Big Bang theory. The light that reaches us from quasars is in fact an after-mirage of the formation of galaxies several billion years ago, shortly after the Big Bang. It thus informs us about the formation of the universe as we know it, but also about the genesis of our own Milky Way. Since it also contains a supermassive black hole, it is likely that a quasar was there at the beginning of its formation. Another theory, a little more unusual, tries to explain the incredible luminosity that results from quasars. According to this theory, quasars are in fact white holes, the opposite of black holes. Instead of absorbing matter, white holes would eject huge amounts of it at a very high speed. This jet of accelerated matter would produce the characteristic light of quasars. But for this hypothesis to be valid, it requires believing in the existence of wormholes, bridges between points in space-time that would allow instantaneous travel from one place to another in the universe. Wormholes would then be found at the center of some black holes and would emerge at the heart of white holes, explaining why the latter reject so much matter. Unfortunately, wormholes remain hypothetical objects, like many others in the bestiary of relativity. But a recent discovery could put everything in question. At the end of 2022, scientists from the University of Caltech in California worked on a quantum computer, that is to say, a computer whose operation is based on the laws of quantum mechanics and particle physics. They have succeeded in creating a miniature wormhole within the Sycamore quantum processor developed by Google. They observed that two distinct groups of particles were connected through a tunnel, causing a particle to instantly migrate from one group to the other. Today, this feat of science is still being studied, but it could well represent a further step in the reconciliation of quantum mechanics with the theory of general relativity. To date, these two models make it possible to explain the laws of physics at the scale of the infinitely small and the infinitely large, respectively. However, a deep incompatibility exists between these two approaches, which scientists are trying to bring together. We have just traveled to quasars, objects that shine billions of light years away. This stopover allowed us to understand that in its infancy, our universe was very active. Galaxies were emerging here and there, gradually filling the void and gathering matter around them. This process of creation gave birth to clusters of forms as diverse as intriguing. If we know that the Milky Way, like Andromeda, is a spiral galaxy, observations of the sky show us that this is not the case for all our neighbors. Indeed, some of them take much more incongruous contours. Spiral galaxies have a flattened disk shape in which spiral arms wrap around a central nucleus. Generally, this core is a supermassive black hole. Rich in gas and dust, the activity within them is strong, so that many stars die and are created at any time. There are also elliptical galaxies. As their name suggests, these have an ellipsoidal shape, similar to a rugby ball. They are generally poorer in gas and stellar dust. Their activity is therefore less. We can say that they are, in a way, galaxies at the end of their life. Even more surprising, the barred spiral galaxies form a flat disk, crossed by a central bar of matter. This is notably the case of the Dwingaloo 1 galaxy, located in the constellation of Cassiopeia. There are several types of barred spiral galaxies, and according to the classifications, ours is also one. Let's also mention the lenticular galaxies, which form a flat disk surrounded by a spherical central nucleus. These galaxies have no spiral arms. The disk of matter surrounding their nucleus is uniform. To make an analogy, we can say that the heart of these galaxies would be like a planet surrounded by a ring of matter, like Saturn. This matter is mainly dust, so that we observe very little star formation. Some argue that these galaxies were once spiral galaxies, but that today they have consumed all their gas and star formation. However, because of their high luminosity, others believe that they are the product of the merger of two galaxies, giving them a large mass, free of spiral arms. There are many types of galaxies in the cosmos, and classifications by shape are not absolute. Some even straddle two distinct shapes, probably because of a galactic merger. This sometimes leads to strange mixtures. We have, for example, galaxies in tidal tail. For these, a bridge of matter is created between two galaxies so that they never merge completely. They thus present two nuclei that leave behind them long trails of matter, forming huge tidal tails. This is the case of the spectacular Idani galaxy. As for the Cartwheel galaxy, it would be the result of the collision of two galaxies, one very large and the other much smaller. The small galaxy would have crossed the larger one in its center and perpendicular to its disk, giving rise to an incredible nesting. Speaking of nesting, it happens that two galaxies never merge completely until they form a very particular cosmic architecture. This is the case of the ARP-143 system, a triangular-shaped structure containing two galaxies in constant interaction. Sometimes it happens that under the effect of gravitation, many spirals of matter are grouped together, forming what is called a cluster. The most famous representative is undoubtedly the Virgo cluster. Located at about 60 million light-years from us, it would contain more than 1,500 galaxies, all within a radius of only 7 million light-years. This is approximately 132 times the diameter of our Milky Way. As you can see, if only in their shape, galaxies are fascinating. This is even more true for the curiosities they contain. But the most curious thing about them is that they are not visible. In fact, we don't even know if this thing is real. It is commonly called dark matter. In the late 1970s, an American astronomer named Vera Rubin became interested in the motions of stars within galaxies. She knew from Newton's laws of motion that bodies orbiting a central point have a slower period of revolution as they move away from it. This is the case for Uranus and Neptune, whose speed of rotation around the Sun is much lower than that of Venus and Mercury. Within a galaxy, the same phenomenon should occur. The more the stars are in the periphery, the more their speed should be slowed down. However, Vera Rubin notes that from a certain point, the speed of stars ends up stagnating as one moves away from the center, instead of constantly decreasing. This unexpected behavior poses a problem of understanding. The most likely hypothesis is that somewhere, lurking in the darkness of the cosmos, there must be a mass of unknown nature, allowing the stars to maintain their speed. It is called dark matter. It would then have the very specific property of not emitting or reflecting light, and of interacting weakly with the other known forms of matter. Its effect would be solely gravitational, thus explaining the structures and movements within galaxies. It is estimated that it makes up 80% of our universe. In other words, this means that we would only be able to understand 20% of our universe, and that within this 20%, many things like black holes still escape our understanding. If we accept the dark matter hypothesis, most of our universe would be hidden from our view. At first, scientists thought that this lack of matter was due to the presence of black holes, exoplanets, brown dwarfs, and neutron stars that we had not yet observed. But after the discovery of fossil radiation, that is, the reminiscences of the first photons emitted in the observable universe, this idea was invalidated. Indeed, the fossil radiation allows us to determine quite accurately the amount of matter known in the universe. And this amount would be far from being sufficient to replace the hypothetical dark matter. At present, the most promising candidates to explain the nature of dark matter are the WIMPs. This stands for Weakly Interacting Massive Particles. Massive particles that interact weakly with ordinary matter. But again, the problem is repeated. If WIMPs do exist, their nature is completely unknown to us. In particle physics, a hypothesis called supersymmetry gives us some answers. For this hypothesis to be valid, it predicts the existence of a bestiary of particles never before observed. One of the goals of the experiments conducted at the CERN particle gas pedal is to find these mysterious elements. If supersymmetric particles are favored by some researchers, it is because they are also a key factor in string theory. This complex theory of particle physics mainly tells us that subatomic elements are in fact made of one-dimensional objects, close to the infinitely small, called strings. It is important to note that currently, no observation has validated the hypothesis of the string theory or dark matter. In addition, some argue that dark matter simply does not exist. The problem would in fact come from the theories that we use, namely the theory of general relativity. Relativity would explain only a part of the physics that governs our world, but it would be incomplete, just like Newtonian mechanics in its time. Still, dark matter does not only explain the structure of galaxies and clusters, it is often associated with its counterpart, dark energy. Also called dark energy, it is another hypothesis explaining the expansion of the universe. To understand it, we must keep in mind that the universe is constantly expanding. On an astronomical scale, all galaxies are moving away from each other. To illustrate this phenomenon with an image, imagine a dotted grid drawn on a balloon. Now imagine blowing up the balloon again and again. You would then see the dots move away from each other as the space expands. In this simplistic example, we are in 2 dimensions, but in the universe, the same phenomenon occurs in all 3 dimensions of space. More surprisingly, the expansion accelerates more and more for galaxies located at the limits of the observable universe. It is to date the only phenomenon whose speed exceeds that of light. Dark energy would therefore be one of the forces explaining this phenomenon of incomprehensible expansion. By taking it into account, we are able to determine the real size of our universe. We know from the fossil record that the universe is about 13.8 billion light-years long. But because the expansion is exceeding the speed of light, photons emitted by even more distant objects have not yet reached us. If we could capture them, we would be able to see the universe in its current state and size. It would measure not 13.8 billion light-years, but 46 billion light-years. An absolutely immeasurable size, which for us is similar to infinity. All this raises even deeper questions. If the universe is expanding, what is it expanding into? Is there another universe with well-defined borders surrounding ours? Or are there simply no boundaries? And if the universe is expanding, what will happen when all the galaxies are separated from each other by billions of light-years? We may never get answers to these questions, but one thing is for sure: we will never stop asking them. We are almost at the end of our interstellar journey. But before we leave, let's take the time to observe some more fascinating discoveries. We talked earlier about the shapes of galaxies, but what about their size? Well, if you turn to the constellation Virgo, you can observe the largest galaxy known to date. IC 1101 is 600 million light-years away and is 6 million light-years across. Compared to it, our Milky Way, barely 100,000 light-years wide, seems ridiculously small. Within it, there are no less than 100,000 billion stars, 250 times more than in the Milky Way, with a total mass estimated at 100,000 billion times that of the Sun. This is quite simply gigantic. It is possible that IC 1101 is the result of successive mergers between several galaxies, but nothing is certain about it. Where things get really dizzying is when you consider that even more monstrous galaxies probably exist, but they have simply never been discovered. IC 1101 is the largest known galaxy, but it is by no means the most distant. This title goes to HD 1. Its distance, 13.5 billion light-years from Earth. Because of its distance, the images that reach us from it show it in a completely new light. Indeed, we are witnessing the beginning of its formation when it was only 300 million years after the Big Bang. To hope to see it, we must look in the direction of the Big Dipper. Since it is still in its infancy, from our perspective, it is a small galaxy. It is only 6,000 light-years long, which makes it ridiculously small compared to IC 1101. But this youth also makes it more active. According to the images we have of it, it produces about 20 times more stars per unit area than the Milky Way. If a few hundred years ago we were still struggling to detect distant stars in our own solar system, like Neptune or Pluto, it is incredible to see how much our ability to scan the cosmos has evolved. Let's hope that the discoveries will continue for many years to come. In the meantime, we can already marvel at what the sky gives us to observe on summer nights. During our journey through the cosmos, we have discovered many artifacts, each more surprising than the other. Between red giants, red dwarfs, and neutron stars, we know that not all stars are as warm as our Sun. Even worse, they can give rise to violent events, such as the formation of stellar black holes and supernova explosions. But they can also end their days peacefully, letting their gases dissipate, and giving the universe the necessary material for the formation of new glowing stars. We have also seen that black holes hold many mysteries. They can form quasars or produce a phenomenal amount of gravitational waves when they collide. They are also an excellent source of imagination for science fiction. By going back to the limits of the observable universe, we have seen that mechanisms that escape our understanding are at work, and at every moment. In a way, we can say that the universe invites us to remain curious. So it is up to us to do everything possible not to disappoint it by constantly trying to pierce the mysteries of the infinite.